Good afternoon and welcome to the Fusion Report Forum. This is our first webinar that we're having. It's called Fusion 2035, the 10-year shot clock. We'll be joined by a number of companies that come from the Fusion ecosystem. Before we get to that, let's go through kind of what how we're going to run this. By the way, my name is Mike Heumann. I'm the Chief Analyst of Condition Research. I'm also Editor-in-Chief of the Fusion. So we're going to have a number of companies presenting today. First will be Commonwealth Fusion Systems. Commonwealth will be represented by Ben Byboth. Following Ben will be Xcimer Energy. Again, the presenter for that will be Connor Galloway. After that, we'll have Peak Nano. John Tomko is a principal product development leader. Peak is a company that builds high temperature films for capacitors, especially for fusion applications. In addition, we'll have Brian Berzin. He's the co-founder and CEO of Thea Energy. We'll also have Regan, who's president and co-founder of Pacific Fusion. We'll also have Alain Becoule. He is the chief scientist and deputy director general of ITER. Finally, we'll have Oded Gorali. He is CEO and co-founder of nT-Tao. We'll also have a video from Helical Fusion, a company in Japan who sent us a short video. Finally, after that, we'll have live panel discussions, and we'll have Q&A and then closing remarks. A couple of ground rules on the webinar. Again, thank you for coming to our webinar. We really think that you'll like this, that you'll find it really interesting, and hopefully very valuable to you. We're going to be recording this webinar, and we'll provide a link to the recording for all the registrants. If you have questions during any of the presentations, put them into the Zoom Q&A window. We'll attempt to answer all these during the Q&A after the panel questions. By the way, when you submit a question, if you have that question directed specifically to a speaker that you're asking about, please put the name of the speaker in your question. As a final notice, we won't be answering questions put in the chat window, so please put them in the Q&A window. Again, thank you for joining us. A couple interesting facts before we go off to our many different people from our ecosystem. The demand for electricity on our planet is growing at an incredible rate. Now, we're used to, at least in the United States and probably in most of the developed world, electrical demand increasing by maybe 0.5% or 1% a year, or even being flat. Okay, over the past 3 or 4 years, that trend has changed dramatically. Most of the projections out there says the demand for electricity in 2050, which you can see on this curve here, will be greater than 2x what it is today. If you look at the colored bars, this shows what US EIA's forecast was on how much electricity could be generated using current sources. So obviously we have a huge gap on that, which we call the electricity generation gap. Okay, that, as you can see, started early, it's starting to increase, and it's going to get very large by the time we get to 2250. Today, the only way we can close that gap is by burning more fossil fuel. That's to generate baseline electrical supply. And baseline, but we mean an electricity supply that can be turned on or off at any given time. If you have renewables such as solar or wind, that can only be done if they have battery systems that are backing them up, which significantly increase the cost of those systems. And that, at least in my mind, is one of the reasons why achieving commercial fusion energy in as near a term as possible is so important. Now, before we turn it over, we'll just turn it over now let's talk a little bit about some of the reasons this demand is increasing. The 2 biggest ones in the United States are data centers, which we've written about in the Fusion report, and also the charging of electrical vehicles. If you go somewhere like China, EVs in particular are a huge part of that demand increase there. Other parts of the world, it tends to be the electrification of industry, the electrification of residential cooling and heating, and commercial cooling and heating. As you can see, this demand leaves a huge gap, well over 12,000 billion kilowatt hours, which is a large amount of electricity. It's probably about a quarter of what we'll need in that time. And with that, let's go over and turn it over to our panel. Thank you very much.
Thank you, Mike. Next up, we're going to hear from Ben from Commonwealth Fusion Systems.
Hello, Fusion fans. My name is Byboth, and I'm the Director of Power Business Development at Commonwealth Fusion Systems. Thank you for the Fusion Report team for the great opportunity to present to you today. It truly is an exciting time to be involved in Fusion, and I can tell you that the team at CFS is working as hard as possible to bring Fusion power to the grid as fast as possible, working around the clock to make it happen. The prompt today's session was about a shot clock. Shot clock is an analogy. In basketball, when the shot clock reaches 0, you lose the chance to score and you turn the ball over to the other team. Framing this analogy to fusion, it might be interpreted that the shot clock could expire if we don't have commercial fusion by 2035. I don't think this is the case. If I were to pick a different analogy, I might pick the white flag that signals the last lap in a long race. This acknowledged the decades of work by the giants whose shoulders we stand on today. The last lap signifies a sprint to the finish line for commercial fusion. A race to establish leadership in any industry, to be the first into the deep blue ocean of commercial fusion. And that leadership matters. The first ones to grab a commercial footing will influence the future of energy substantially. China's advancing fast has made progress rapidly up the pack in the last few laps, but I'm confident that fusion will see the finish line. And for all the reasons that the shot clock will not expire, that may be just the start of another race to scale. Before I jump into the CFS approach, I want to revisit why I don't think the shot clock is going to expire and result in a turnover to another technology. We are in the middle of the largest industrial transformation in history, and there are lots of different projections for clean energy demand. And while they may agree or disagree, what they all do agree on is that it's going up tremendously, potentially even doubling by 2035 already. And this is being driven by the electrification of everything from intelligence to industry to transportation to heating and cooling. The more you think energy is a technology and not a resource constraint, the steeper the line on the graph. This graph is in gigawatts, but you can generally translate that to gigadollars, which is an enormous opportunity, a multi-trillion-dollar opportunity. We're going to need to build about 3,700 new power plants to replace the existing ones. And that's not even considering what would happen if the energy demand were to double. Those 3,700 power plants that make up 85% of the world today generate about $1.8 trillion a year in revenue. So a tremendous opportunity. And if you look across a range of technology options that could potentially provide for this, almost every available technology, existing or emerging, has some sort of trade-off, be it the reliability or the siting availability, or even just the cost in general. Only fusion has the potential to check all of the boxes. Really, the only problem with fusion is it's not here yet today. If it was, we would sell a lot of fusion power plants. And there are great things happening in the fusion industry. The Fusion Industry Association members have now raised more than $10 billion in private capital across a wide range of architectures. And this investment is being turned into research and progress at the speed of the private sector. To revisit the racing analogy, we now have a lot of fast cars on the track, increasing the chances of success. And behind those crews are the sponsors and investments necessary to keep them moving and to get them going faster. And while it's not here yet, there's been tremendous progress on key fusion metrics at a pace that's faster than Moore's law. That progress stalled with the fundamental limits of key pieces of technologies. For CFS, it was magnets. For others, it may be lasers or capacitor banks, or new simulation capacity, or new materials. All those advancements are arriving now and adding to the progress of the past and providing the path forward for commercial fusion. And so I do think that we'll have commercial fusion before 2035. And CFS has been formed with the intent and purpose to do this. We have an approach based on proven plasma physics that's been peer-reviewed and delivered by the largest fusion company with now over 1,000 people and more than $2 billion invested, and a team that knows what it's like to build hard things and knows what it means to manufacture at scale, who is actively engaged not just in the technology development, but the ecosystem development, spearheading a regulatory path now codified into law where fusion plants will be regulated not like fission plants, but like particle accelerators. The licensing can take a year or two, and that's a big improvement from the 10 years and $1 billion for legacy nuclear fission plants. And at CFS, we've taken a deliberate and systematic approach to risk retirement, starting with the physics that from the MIT's Plasma Science and Fusion Center, and then moving to the magnet technology, which we demonstrated. And not only did we demonstrate that, we demonstrated the ability to stand up a manufacturing line to build these novel technologies. And now we're integrating that known architecture with these new breakthrough magnets and our device Spark here in Massachusetts. And that project's now about 65% complete. And then beyond that, we've already started the work on our ARC, our commercial power plant. In CFS, we've decided to vertically integrate on the key technologies that we need. We're operating our first factory now. Over 100,000 square foot of manufacturing in Massachusetts with technicians working around the clock making magnets that will be used in Spark. These magnets are some of the strongest in the world. And we don't only just make the magnets here, we also have all of the test stands to make sure they're made with quality and provide the quality assurance we need to know they'll do what we need them to do when we need them to do it. And I'll show in some pictures here. You can see some of our technicians working to meticulously insert some of the first superconductors into some of the first pancakes that will go into some of the first magnets for Spark. Or those pancakes stacked together to bake the big magnets with the machines that put them in the right cases. And the cases that can withstand the enormous force that comes from magnets with tens of thousands of amps of current flowing through them. And the types of test stands necessary to show those magnets work. And those magnets are going into Spark, our pilot plant. This is an actual picture of the machine, not a rendering. It's more than 65% complete and on pace for operations in 2027. Spark shows that a company like CFS can architect and engineer these types of machines, and that regional constructors and local talent, not the super majors, can construct a fusion machine. It includes a supply chain that stretches across 31 countries. Beyond the technology inside, which is truly impressive, Spark is the proof point that CFS can execute on complex billion-dollar scale projects. And we have confidence that Spark is going to work. Self-critique is a core value of CFS, and from the beginning, CFS has been committed to holding itself accountable to science, engineering, and commercial progress. One of the ways we do this is through the peer review process. Since our inception, we have published more than 60 papers and journals detailing out our science and engineering advancements. We use this to provide confidence to the scientific community, to our investors, and to ourselves that the fusion machines we are designing are going to work as intended. But as I said, Spark is really about demonstrating that ability to execute. So Commonwealth Fusion Systems took over the role of architect engineer for Spark, and since then has now generated tens of thousands of work order packages to our construction partners to deliver. And in order to do this on the timelines that we're looking to, we must execute with the highest level of quality. And what we've seen is that we're through that 15,000 work orders that have been done, we're now running about a 0.5% construction rework cost to date. That's exceptional. That's better than residential. It's way better than what happens in heavy industry. And it's a proof point at our ability to deliver these projects as designed and as engineered. And these things we're building, they're not little things. These are big, complicated things. Integrated and connected things. But things that borrow from other industries, like these large compressors that are similar to what's used in liquefied natural gas to be able to deliver the cryogenic fluid to keep our magnets cold, to confine the plasmas. And these are systems now that are being commissioned. So we have fluid in systems. We're running pumps, we're running valves, venting systems, turning them on, turning them off, getting operations instructions written for all these systems in order to support the tokamak operations. As we move from building and system support construction and into tokamak assembly, a lot of the long lead part items that we've ordered many months ago are now starting to get ready for shipment to CFS. And ensuring the quality of those parts and those vendors around the world has been a big effort. So when I said there may be 31 countries that are in the supply chain, on a given day, CFS has an employee in about 15 different countries working with our suppliers, ensuring these items are going to be delivered as expected. And Spark will pave the way for ARC. Of the 17 systems that you need to make a power plant, 13 of them will be demonstrated at appropriate scale inside of Spark. And the remaining systems are being tested and demonstrated in other experiments. Spark also will give us a lot of confidence in the commercial viability of ARC. Because we've been able to collect the receipts from over $1 billion spent, we now know how to make all of the major components that we'll need for ARC, and we know how to talk to our suppliers to gain the estimates and cost, to give confidence to our investors that we are going to be able to build commercially relevant and commercially viable fusion power plants in the future. And while we continue to work on Spark, a lot of our focus is moving towards ARC. This is where I spend most of my time thinking about. ARC will be our commercial power plant. This will be the one that we expect to have on the grid in the early 2030s, before this 2035 shot clock. It'll be about a 400 megawatt electric power plant that can be connected to the grid as a grid scale asset that can be flexible. We can ramp it up or ramp it down. We're working on the process now of getting that line for interconnection with the PJM grid. And we're really excited about the potential and the site that we've got picked out for it. That site is an ideal site for the first commercial fusion power plant. Located about 20 minutes south of Richmond, about an hour and a half south of Washington, D.C. Located adjacent to a coal plant near the James River and I-95 for logistics with a rail spur attached. It really is an ideal site for a first power plant. But beyond that, it's also the site of some tremendous partnerships with the state and the county, and a lot of work going on to educate and inform our residents and our neighbors as we get ready to build our first power plant. And that project's very much under development now. We have an active zoning case. We're meeting and engaging with the county and the officials and the community to get ready for that. So it's very much steps taken towards the permitting and actual development of that project. And work's underway on the detailed design of ARC today. And here's a first rendering of what the plant may look like, sitting on about 25 acres of built-out land, connecting for the first time a steam turbine to a fusion device to make electricity and put that onto the grid in Chesterfield County, Virginia. But in order to have a commercial industry, it's more than just a technology. One of the things I've been most impressed about my time here at CFS has been the thoughtful approach to building not just a technology, not just a company, or not even just an industry, but a real movement around fusion. And that movement for fusion requires educating and engaging stakeholders that range from the next door neighbor here in Devens that's about a quarter mile away, to heads of state and governors and leaders. And in between, there's a lot of people who we work with in the form of the communities, with our supply chain, with the builders and technicians and constructors of our machines. And that's a global approach to building a movement, not just here in the United States, reaching out to global leaders to try to enforce and develop the right types of regulatory frameworks necessary for fusion. One of those key stakeholders is the regulator. And the long work that's gone into educating and teaching them about the safety of fusion, both in the United Kingdom and the United States, now has us with a framework of appropriate regulations that we can use here to grow an industry, but also can be the template for other countries to take up fusion. And these regulations are not just regulatory here in the United States, they've also been codified into law, ensuring the type of stability that we think we're going to need to grow an industry. And these regulations allow for the competitive differentiation of what fusion can do as a clean energy resource. So it allows us to maintain and standardize our devices and assets as much as possible to keep costs down, to reduce the dollars per megawatt hour, which is really the goal for commercial fusion. I work on the commercial side of the organization here at CFS. And as we thought about the approach to commercial fusion, we laid out a bold vision years ago. It started with a vision that siting could be the start of it. So cite it and they will come was kind of the mantra. And that set us on a 2-year search to find the optimal site, as I mentioned before, in Virginia. In addition to that, we knew that there would need to be a customer who could send a signal that represented the incredible demand for fusion and its attributes and its ability to provide that clean energy that's so much in demand that I talked to at the beginning. And along the way, we thought maybe we could find a utility partner, and maybe they wouldn't be engaged early, but maybe we could get them started on the pathway. We could get onto integrated resource plans. We could start to work with them so they could understand the technology and reduce the time necessary to get our products to market. And then all that would come together with the proof points of the technology to de-risk the future for finance and for investors. And so where we stand today, we made a lot of progress on this goal. And so step one for our journey was siting. And we were, again, very lucky to find the site we did in Virginia. And that with that site came a real partnership. And for all the reasons I talked about before, from just a fundamental interconnection point to the grid and as a fundamental infrastructure environment, it was one of the best we found. But it goes beyond that. We found an environment with an extremely talented workforce that was excited about energy. And for us, seeing the opportunity to be a part of this state that's really at the vanguard of a clean energy transition that has growing load demand and a desire for reliable, affordable, and ever cleaner power really had us excited about the opportunity to be a part of what was happening in Virginia. And so also in the site in Virginia, we also have a partner in Dominion Energy. And Dominion Energy is one of the largest utility companies in the country, and showing that you can execute on big projects and innovative things like their work on offshore wind. And so we're excited to partner with Dominion in a joint development agreement that we announced alongside the siting announcement. And that agreement includes, one, the lease of the property, because it's Dominion-owned land that we'll be developing ARC on, but it also includes a partnership to look at how we can learn about operating power plants and connecting them to the grid and lots of great things. And at the same time, we can teach about fusion. And so as I had said, we had hoped that we'd find a partner for some future plant. We were really excited to find one for the very first one, and really excited to partner with the Dominion Energy team as we go forward. In June of this year, Google and Commonwealth Fusion Systems announced a new global milestone, a bold partnership to develop, deploy, and scale clean, secure fusion power. Google signed a power purchase agreement for about 200 megawatts of electricity from our first ARC power plant. Google's also included an option to offtake power from additional ARC power plants. An investor since 2021, Google also deepened its relationship with CFS and increased its investment. We're really proud to have a partner like Google who's had such a long legacy of leadership in advancing clean energy technologies and helping to lead through their procurement of clean energy and the energy transition. And so with now customers that demonstrate the demand for fusion and a site and a utility partner, we've now done a lot to de-risk the potential pathways for commercial fusion, combined with a movement and an opportunity for appropriate regulations and stakeholder engagement with a technology that continues to rapidly advance. We're in a really good spot now to move after Spark, raise the type of money that's going to be necessary to build and construct that first power plant. And that's a great opportunity for continued innovation in how we think about financing first-of-a-kind projects. But as CFS has shown across the board, we're not intimidated by the need to take on challenges with first-of-a-kind projects. And we look forward to what those outcomes will bring in the future. And so with that, as we kind of wrap up the presentation here, I'll move to close with the same slide I've closed all of my presentations with, which is to imagine this world with no constraints enabled by fusion. And I firmly believe that we will have fusion on the grid before 2035. But I also believe that that's not the end of anything. It's the start of the efforts to scale and grow the industry, to be able to provide the type of benefits that we've all talked about for fusion now for decades. So super excited about what's to come, and I look forward to catching up with all of you on the end of the presentations for some questions. Thanks again. Talk to you soon.
Thank you, Ben. Next up, we're going to hear from Connor from Xcimer Energy.
Hello, everyone, and thank you, Mike, for hosting this event. I'm excited to talk a little bit about Xcimer and our position on the fusion industry in general. My name is Connor Galloway, and I was roommates at MIT with my co-founder, Alex Valys. My background is physics and nuclear engineering, and I've been working in the field ever since 2009 as a graduate student at the Plasma Science and Fusion Center and Los Alamos. So at Xcimer, we do believe there is a path to electrons on the grid by the mid-2030s, both for the industry as a whole, as well as for our specific path forward at Xcimer. But of course, there are challenges ahead. So I'm going to tell you a little bit about our path at Xcimer, our next steps to get there, our progress to date, and then conclude with a few thoughts on fusion industry challenges. So we have raised at Xcimer over $100 million in Series A capital, and we also won the second largest award in the Milestone Fusion program, next to Commonwealth Fusion Systems. We have 75,000 square feet of laboratory space in Denver, Colorado, over 90 employees, and we founded the company in 2022. And that's our current facility there you see in the picture with the Front Range in the background. That is where we're building our prototype laser system, Phoenix, which I'll talk about a little bit later, as well as all of our office space for the company. So we are building a commercial pathway for the most proven fusion approach, namely hotspot ignited laser inertial fusion. This is what worked on the NIF, was demonstrated recently, but solid-state laser technologies such as those used on the NIF are too costly to scale for commercialization. So at Xcimer, we are using a lesser-known alternative to solid-state architectures, gas Xcimer lasers, hence the name of the company, just without the E, which are much more affordable in scaling to the energy levels needed for achieving robust commercial gain for inertial fusion, and the low cost can enable great economics to where we have a path to producing electricity at with a COE of $50 per megawatt hour. So as I mentioned, laser inertial fusion is the only technology to date to surpass scientific break-even and produce a fully self-sustained burning plasma, where here is the performance of some fusion machines with tokamaks there, and then NIF laser inertial. And the record gain so far in NIF is a gain of 4.6. So just past April, the NIF achieved 8.6 megajoules of fusion energy out of a fuel capsule with 2 megajoules of energy that were utilized to drive the system. So amazing achievement. What motivated myself and Alex to get started in inertial fusion was actually when we learned about what was called the Halite Centurion test program in the 1980s. And this is not often discussed and not well known, but high gain inertial fusion was demonstrated during this program. The key difference here compared to NIF was that in these experiments, X-rays generated from nuclear detonations underground at the Nevada test site were used to drive and implode laboratory scale fuel capsules. These experiments were successful, and the official statement from DOE is there saying experiments conducted at the Nevada test site have demonstrated excellent performance, putting to rest fundamental questions about the basic feasibility of achieving high gain. And the details are classified, but Los Alamos National Lab, Lawrence Livermore, and the National Academy of Sciences all recommended the development of a laser architecture that could scale to 10 megajoule illumination, and that would be sufficient to replicate the conditions in these successful shots. So we're fortunate, based on these experiments, that we know a 10 megajoule laser is sufficient enough energy to enable commercial gain. And importantly, the NIF, National Ignition Facility, is only 2 megajoules because of the very high cost of the solid-state laser architectures that impede them from ever scaling up to 10 megajoules. So back to the National Ignition Facility. So here, there's 192 beam lines that you see here in the picture, and all of these beam lines are directed to a target chamber and ultimately a whole Raman fusion fuel capsule, and you see the picture here in the bottom right. The way NIF works is the laser energy is used to illuminate the inside of a heavy metal can, and the laser energy is converted into X-rays inside this can. And it's actually the X-rays that absorb on the fuel capsule you see here in the middle. It's kind of sub-BB sized ball. And it's the X-rays that drive the implosion. And it's important to note that this process is roughly about 12% efficient, and it's called indirect drive. So on the NIF, while there's 2 megajoules of energy in the laser, only about 250 kilojoules is actually absorbed, on the fuel capsule. And this depicts the general process. That energy is absorbed on the fuel capsule in the plastic ablator, and then the deuterium, tritium, hydrogen fuel is inside that. The plastic heats tens of millions of degrees, blows off, and the fuel capsule is imploded, compressed, and is ignited, and a self-sustained burn wave is initiated. And what's very important and significant for the NIF is that the gain of that fuel capsule was 34. So they produced 8.6 megajoules of fusion energy on the record shot, with only 250 kilojoules coupled to the actual fuel capsule. So what we're doing differently than NIF is we have a different illumination geometry, and we're shooting a much larger fuel capsule. So here on the left, you see NIF with 192 beams. We're just going to use 2 beams with much higher energy. And so we'll be able to couple over 8 megajoules to the fuel capsule, whereas NIF is only coupling 250 kilojoules. And the way we can do this is we can beam shape our laser beams to where they're peaked around the intensity, the intensity around the ring of the laser spot is higher in intensity by about 2-to-1 contrast. So when you do this and you absorb the laser in the target plasma corona, you can get spherical implosion from two-sided illumination. And we published a paper on this target design concept with all three major design labs, Livermore, Los Alamos, and the Laboratory for Laser Energetics and General Atomics. And it was an editor's pick in physics of plasma. So I encourage anyone interested to dive in to read the paper. So of course, how do we get to coupling over 8 megajoules to the actual fuel capsule? And we need to lower laser cost. And that's what we're all about at Xcimer Energy. So we're cutting laser costs by replacing glass with gas to enable commercial IFE. And this is an illustration of one beamline where we start with what are called long pulse KrF laser amplifiers operating at about a microsecond. And then steps 2, 3, and 4 are a way we can compress this energy in space and time to the nanoseconds needed for fusion illumination. So steps 2, 3, and 4, these are nonlinear optical processes, and they act like gas mirrors, reflecting the laser light, compressing it in space, compressing it in time, and sending the high energy beams into a target chamber. So here you see our two-sided illumination inside this chamber, which uses a thick liquid wall to protect the steel of the chamber. And coming to that, so this is that chamber with the laser abstracted away. So we will, utilizing 2-beam illumination and less than 1 Hertz shot rate, enables the use of thick liquid wall protection based on the high life design, which was developed in the early days of Livermore in the late 70s and early 80s. So what's great about our approach specifically is with the small number of penetrations and low repetition rate, we can use FLIBE, which is our coolant and tritium breeding material. We can also use it as a first wall protector. So the chamber can last the lifetime of the plant. And we can use currently qualified steels in the construction of the reactor, which is a major advantage. So we'll be shooting one target every few seconds, few gigajoule yield per burst, and collecting the energy in the FLIBE, which then you have to extract the tritium to drive to fill future targets, and then take the heat away from the FLIBE to power a standard steam cycle. So in summary, lower laser cost enables us to build a much higher laser energy than NIF. This enables us to shoot much bigger targets in the robust gain regime of the Halite Centurion experiments to achieve commercially relevant gain. And the laser architecture enables us to use thick liquid wall protection so that our chamber can last the lifetime of the plant. And this is our roadmap to how we can drive the cost of an nth-of-a-kind plant down to $50 per megawatt hour. So our roadmap, 3 major phases. The first phase, Phoenix, is where we're demonstrating this gas optic, this gas mirror technology that I described earlier, as well as demonstrating that we can build KrF lasers at a microsecond plus pulse length, and we really understand how those lasers operate. The next major phase of our program is Vulcan. This is our break-even machine, where with a 4 megajoule laser, we'll achieve wall plug break-even. So that means more fusion energy out of the burst than the laser took off the grid electrically. This system will be upgradable in place directly to 12 megajoules, where we'll be able to serve several national security applications, such as stockpile stewardship and nuclear weapons effects testing in this Vulcan break-even machine. And then finally, by the mid-2030s, we'll build Athena, which is our fusion pilot plant to deliver electrons on the grid. This is showing a depiction of the progression of our Xcimer or KrF laser technology. The first 2 steps are part of the Phoenix program that I just showed on the prior slide. The Argos module is part of Vulcan and Athena. So Argos is what we will mass produce, which mass produce these laser modules for all future systems. And the LPK stands for long pulse kinetics, and the kilojoule system are our prototype systems that will enable us to develop new pulse power technologies and benchmark all of our laser codes so we can design the Argos module. Here is an illustration of the Phoenix system. Shown in green is complete. Shown in yellow, we have prototypes complete, and then the rest will be completed by Q2 of next year. And here you see a central feature of the Phoenix architecture where we have, as shown in purple, is a long pulse, in this case in Phoenix, a 250 nanosecond pulse. And then that has a lot of energy. And then here a short pulse that has much, much less energy, shown in orange. These beams counterpropagate, and energy is transferred from the beam shown in purple to the beam shown in orange. So as the orange beam crosses that purple beam, it takes energy away from the purple beam, so it effectively reflects laser energy, and it's compressing it in time because the energy is transferred to a shorter beam. LPK, here's a picture of a before and after. So on the upper left is an early design shown virtually in place before we raised our Series A. And then we completed this on time and on budget by the end of last year, and it is now fully operating, and we're actively benchmarking our laser codes and informing the design of the Argos laser module. So switching gears a little bit to thinking about what is needed for fusion on the grid by 2035. So first, fusion performance. I think most approaches require a break-even demonstrator along the way. You have Spark for CFS, you have Vulkan for us. Other approaches have similar concepts. So it is really important for a given approach to demonstrate wall plug or facility or engineering break even. All those terms are very synonymous. Finally, experience. Fusion startups need to learn by doing. And this is important because the past major big machines like the Z machine, the Jet Tokamak, NIF, one, these were all built decades ago. So the designers and builders have retired, and these were one-offs. So industries were not, supply chains were not industrialized to support mass manufacture of the components for these one-off machines. So companies have to learn by doing. Companies have to not just learn how to build complex machines, but learn how to build teams that can build the complex machines. And this takes a lot of iteration. And this is sometimes often overlooked in thinking about timelines. Also, talent. You need the best people in the world. And as I mentioned, there's a lot of great scientists who worked on the development of the machines in the government decades ago that are now in their 70s and even older. And so companies need to consult with these individuals and help them educate younger generation of workers at the companies for knowledge transfer, especially for Xcimer. A lot of our technology was originally developed in the 1980s during the Cold War. So we have several people who worked on laser missile defense projects where that was well funded back then and not now, of course, helping train and educate younger generation of workforce at Xcimer. And then finally, money. Of order, it's a few $1 billion per mature scientific approach to get to electrons on the grid. And that's a lot of money. And typical VC models are very gated. You tackle the high risk things first before deploying a lot of capital to move forward. And in fusion, to get there by the mid 2030s, a lot of parallel development has to go at the same time. Not just the major de-risking like fusion performance or engineering break even, but supply chains and other lower risk technologies, such as fly pumps, et cetera, but technologies that need significant capital to develop. So government investment can encourage more risk taking from investors and enable more parallel path development, which will be needed to reach our goals of mid-2030s deploying electrons on the grid. Finally, the long lead items for commercial fusion. Of course, tritium technology, all companies will require large-scale tritium handling, at least a few hundred grams of tritium or more, and no fusion pilot plant has built to date with tritium systems in place. So that technology needs to be scaled and is shared among all companies burning DT, which our position is all the first power plants are going to be DT based. Of course, raw materials, the big ones are lithium, beryllium. These are blanket materials. Depending on approach, whether it's fly, beryllium, lead, there are a lot of mass of raw materials are needed to build the blankets for these machines. Solid state switches used by all pulse power approaches, including Xcimer Energy, because our lasers are pulse power devices. And this technology development is a 5 to 10 year time frame. And finally, construction, siting, permitting. States need to get educated on how to license not just reactors, but break-even machines. And this takes time and design cycles. Finally, wanted to comment, fusion is a global race, and China is moving fast. China is currently building a larger version of NIF in Pyongyang. There's a lot of debate as to what energy level this will be at, but seems like it will definitely be over 3 megajoules, and they have the billions to spend to build a solid state system at several megajoules of energy. And Xcimer, on the laser side, our company is the only path for the US to compete on both speed and laser energy in order to compete with China. Because if China builds this, they're going to have a stockpile stewardship capability that surpasses the United States. So it's not just energy security, but also other national security items that the US needs to be concerned about with respect to China. And then finally, to conclude, we need more money in the Milestone Fusion program. There's $50 million were allocated to 8 companies. And in the NASA COTS program, it was roughly $500 million that went to 2 companies. So we really need to step up our game in the United States, educate members of Congress, and educate the public of the importance of public-private partnerships and bring more money into the program. And with that, I'll conclude and thank you everyone for listening to me talk a little bit about Xcimer and our views on the fusion industry. Thank you.
Thank you, Connor. Next up, we're going to hear from John, coming to us from Peak Nano.
Hi, my name is John Tomko, and I'm the Principal Product Development Leader for Capacitor Film here at Peak Nano. We're a supply chain company that's working on providing a solution to power handling, particularly in the form of vastly improved dielectric film in order to replace current polypropylene capacitors. I say all that, I know that's different for most of the fusion folks. Hopefully this kind of ties in later on and we see the importance of this. However, I think the outline for this should be pretty straightforward. Because like I mentioned, we're not a mainstream fusion company like most of the presentations. I thought it'd be useful to get some additional information on Peak Nano and our efforts overall. And this will hopefully naturally segue into a discussion about our core technology and how it's really differentiated from current market options, with particular emphasis on how this fits into the fusion ecosystem. I'll then wrap this up in the form of more discussion on really fitting into that ecosystem further by providing context on our experience with the fusion supply chain in areas where at least I think we can put particular emphasis within the fusion community to improve the supply chain as a whole. And so I'll start with Peak's introduction with this really nice slide from our marketing team. We have this mission statement of delivering nanoscale technology with macro-scale benefits in a number of sectors. And really what this means is that we're using a bottom-up approach to material design that allows us to make a new material that fits into pre-existing systems. It's really a drop-in replacement. We aren't trying to make new quantum computers or anything like that. When you think of metamaterials, you'll still end up with a complete macro-scale capacitor in this case, of what I'll be talking about today. It just turns out that this layered metamaterial-based design really gives you a lot better net properties than what you might find on the market right now. And so we've been on a fairly decent run with this technology so far. Peak Nano's been producing materials since about 2016. And this is really thanks to a decent amount of capital investment that really allowed us to expedite that timeline from research through development and into production status. And this is really seen in terms of manufacturing capabilities by our 75,000 square feet facilities, which houses about 125 employees. I say that we're always in the process of continuously scaling to manufacture even more material. But we're even more proud to say that we're a fully US-based manufacturing company. And so we can really offer a fully domestic supply chain, which is relevant to a lot of the companies here, I imagine. We'll discuss this more in the technology overview, but this is really enabled by a very unique approach in which we create a layered material design. And so by varying the materials within the layers as well as their thicknesses, we can really achieve a wide range of property tuning that you just can't achieve with single materials, blends of materials, or even alloys of materials. And so one of the key benefits of this material tunability that we can enable is that it naturally lends itself towards multiple application spaces very easily. And so we can readily kind of vary this material design to fit a given application as needed. And so the technology I'll show you today is primarily focused around energy applications, particularly film for capacitors, but we're active in a number of other verticals, including packaging, optics, and aerospace, all of which are really enabled by the same design principles I'll be showing you here today. And so I think that's enough marketing for now. What's Peak Nano actually making, and how is this relevant to what we're doing here in the fusion community? Our core technology is really what we call nanoplex film. And so typically when we think of dielectric materials or plastics, they're really composed of a single material system. Maybe if you're really advanced, you might figure out some clever blend of two polymers. But primarily due to manufacturing challenges and technological incompatibilities with a given application, you usually find that you can only get so far with these types of approaches. And so what Peak Nano's instead developed is this co-extrusion process shown here that's scaled to production levels already. So this isn't R&D in a university lab anymore. And it really directly enables these multi-layered materials over tens to hundreds of thousands of meters without issue, which is necessary for the scales of manufacturing we're talking about here. And really what this is just a polymeric superlattice. And so what that's doing is effectively taking two polymers, in this case polymer A and B, and alternate stacks of them within a single plastic film. And so we can usually vary the layer numbers anywhere between 10 layers, or the most we typically do for manufacturing is 4,092 layers, sandwiched within usually a few microns. And so you're looking at much less than 100 nanometer thicknesses per individual layer. And so what you can imagine is these individual layers enable kind of unique properties relative to their bulk counterparts. And so just to show that this kind of actually works, I just pulled in this nice SEM micrograph of a local region, where you can really see the nice homogeneity of the layers and nice repeatability. And so one example of this in kind of a more practical sense is that we can take two resins and make a film with extremely high dielectric constants, up to about 5. These have extremely limited leakage currents, and so this really enables extremely high energy densities relative to if you were just to take a single resin, make it bulk, and the properties you might find with something like polypropylene, which is the current standard, and we'll talk a little bit more about that. And so really this film is now tuned for pulse power applications, but again, the benefit to this layer design is that I can then take two different resins and give you a completely different material system with its own set of properties that is still better than the market standard, just maybe in a different way. And so, for example, here we can take another series of film using two different resins, A's and B's, and make a different material that we call LDF, or low dissipation factor. And so this is really designed to generate significantly less heat. It's really designed for high current applications, and generally outperforms polypropylene in most scenarios where you're really trying to push the limits of how much you can get out of a capacitor. And so more importantly, even if we're ignoring how much heat is generated, let's say it does generate the same amount of heat as polypropylene, this material is designed to have complete stability across the entire operational temperature range. So in most dielectrics, again, using polypropylene as our example, just because it's the standard, you tend to see that as soon as they hit the 100 C mark or so, you have to derate them by 50%. And so you buy a 1 microfarad capacitor, you're now running it at 0.5 microfarads with half the net voltage, which obviously leads to instabilities in your network. And that's not ambient temperature, that's hotspot temperature. And so in most cases, that's an unavoidable process, again, especially when you're talking about high current applications. And so this LDF film really has the benefit that it has constant operational properties, even when these hotspots begin to form. And so you start to gain constant kind of electrical engineering capabilities over its whole lifetime. And so, again, the current industry standard I keep mentioning, polypropylene, specifically what I'm now going to refer to as biaxially oriented polypropylene, or BOP, just for simplicity. This is where polypropylene is extruded into these extremely long sheets of plastic. Again, we're talking 40,000 meters length is typically the manufacturing limit for these. And then we take that film and stretch it along both axes. And this stretching process, this biaxial orientation, really is orienting the crystalline domains within the material. And so in doing so, you take a kind of a okay dielectric material like polypropylene, and you give it significantly better dielectric properties. BOP is pretty much the standard across the world for all energy applications. If you go to the grid, for example, you'll see these large substations, which are running hundreds of BOP-based capacitors. And the reason for this is mostly because you can intrinsically scale the manufacturing to this as needed, and it gives you the dielectric properties that are pretty okay. And again, just for a sense of the manufacturing scale, we're talking about probably about 1 billion pounds of material a year just in power generation. And so again, this is because you have BOP's excellent manufacturability. It has pretty good room temperature dielectric properties. But even with all that being said, it still has a slide for now. And those limitations really come in the form when we're comparing our BOP-based capacitor to peak nanoplex film at a capacitor level. It's a lot to talk about film. It's very different for us to start thinking about how this ends up in our actual device. And so one of the first benefits, again, is this higher operating temperature regime. This essentially means not that you're running it out in the hot desert or in more extreme ambient conditions. It can do that. But even if I have a well-controlled environment, it means I can essentially run the capacitor harder. I can put more net current through it because it can tolerate the amount of heat generation. So even if the two materials produce the same amount of heat, I end up with this fact that I can just run it harder. In the case of our high dielectric constant material for pulse power, that HDC film I was mentioning, again, really nice parallel to BOP, just slightly different application space. For pulse power, the energy storage differential between this and polypropylene basically lets you create a significantly smaller net size capacitor housing. When you start talking about costs of capacitor, that starts to matter a lot. Even though you're only, these capacitors, if you look at pulse power applications at Cap Bank, each of these might be 100 pounds of film. It turns out that's actually a small cost of the net capacitor. Most of the cost comes in the form of the housing. And so it starts to matter a lot when I'm buying thousands of these capacitors to power my system. If I can reduce the energy density of each one, the net cost ends up being significantly improved. And so looking at both of these films, just as easy examples, LDF and HDC, really the main advantage is the ability to extend the lifetime under equivalent operating conditions. And so what I mean by this is if we run a BOP capacitor in the same way that we run these two films, you'll see that these vastly outlast in terms of net lifetime, which means we have less capacitor failures and we have less capacitor replacements over time. And so your system's running better for longer without needing, manual input. And it also means I'm saving a lot on my capital costs just because I'm not replacing these capacitors at very high frequencies like you do at most high power systems right now. And so, again, a really good example of this is HDC. I'm going to kind of jump back and forth between the two material systems. This is, again, the high dielectric constant. We can kind of see the variety of properties here. As soon as HDC is compared to BOP, we're getting a factor of 4 volume reduction just because of the improved energy density of this raw film. And so this isn't to say it's the perfect material and that there's no trade-off. You can't put this in every application, just to be very clear. There's a measurable increase in the dissipation factor. Now I say that's not all that matters. You can play some tricks to improve your equivalent series resistance. However, for pulse power applications, when energy storage density really is your primary factor, this becomes an excellent material system compared to BOP. And again, you can kind of tune the properties between 3.7 and about 5-ish when we're looking at kind of the different product ranges peak nano offers. And so again, you have that aspect of tunability for different material systems or needs in the power grid. When we're talking about non-pulsed applications, so again, when we're running at really high frequencies or just DC current applications, you're really talking about heat resistance as being the primary factor of interest. And so I'm intentionally kind of using the term heat resistance very loosely by intention because it's a really nuanced aspect when we start thinking about it. In some situations, like in power electronics, where we're implementing silicon carbide everywhere, and it's naturally being pushed to 200C operational limits, I'm using heat resistance in that case in the form of whether the film can sustain the same operational temperature as the device itself. Because what happens if you can do that, I remove the need for active cooling. In other words, my capacitor can run at 200C or at very high temperatures. I don't need to implement active cooling. My engineering constraints are simply reduced. But again, there's also this hidden secret on the longevity of the capacitor in terms of heat resistance. And so when the capacitor is run at any temperature above room temperature, BOP gradually gains a derating factor where its capabilities are reduced from room temperature. And then, of course, just from internal heating, the temperature of the capacitor can easily reach 100C in terms of hot spots, which leads to deratings. Now, this derating isn't usually in the form of lower operational voltages, but it also leads to reductions in lifetime. And so, for example, if you run a BOP capacitor with a 100C hotspot, not 100C ambient, just a hotspot, so again, high current applications, its operational lifetime reduces by orders of magnitude. You'll see most capacitors with a hotspot of 100 C, which is easily reached for, again, the currents you need for a high HTS magnet, might be 500 hours if you're lucky. And so again, this becomes a major constraint on what you can get in terms of your net lifetime. And so when we compare that to kind of Peak's product, LDF in particular, this really acts as a drop-in replacement for BOP. But again, with this idea of really improved thermal stability, where we can sustain temperatures of up to about 135 C. That's ambient temperature. That's not even hotspot. You go quite a bit hotter in terms of hotspot, actually. But what you, again, find is that you don't have to derate the material, and that its lifetime at high temperature is much closer to its room temperature lifetime. Again, so you gain lifetime, and you gain a lack of derating. So just to highlight this a little more clearly, we can consider two capacitors made identically with our LDF film versus traditional BOP. In the case of BOP, we can see that the capacitor actually has to be derated by over 30% at 125 C, whereas Peak Nano's LDF film only loses 5% of its peak performance. And the same is true for that HDC filmed energy storage density or capacitance, which can operate significantly hotter. And so again, this increased cutoff limit on the max operating temperature leads to a direct correlation in the net lifetime of the capacitor, where small hotspots in the device, in the case of LDF, don't lead to detrimental thermal runaway, just because the capacitor can be more tolerant to these conditions. And so this thermal stability is really the direct result of Peak Nano's core technology, which is that production of nano-layered polymeric films. In the case of LDF, the direct drop-in replacement for BOP, we have much better lifetimes and thermal stabilities. This is actually achieved by taking the same polypropylene you find in every other capacitor, cap-grade polypropylene, and layering it against a high glass transition glassy polymer. And in doing so, the polypropylene effectively becomes stuck within these rigid, well-defined boundary layers. And so this means as temperature or other stresses are applied to the film, like high voltages, the material essentially resists strain and becomes really locked into this well, and gives you constant performance. Because the material is primarily polypropylene, again, it means that the cost is actually very comparable to BOP, and it really just drops into the same capacitor system with minimal additional effort on the engineering side. And so now I'm saying all of this, I showed that nice SEM micrograph early on, and I'm really used to seeing micrographs of this perfect 100 nanometer region of a super lattice, and everyone calls it the next big thing in their Nature paper, and then you never see it go anywhere, mostly because we all know that if you move a little bit over, you'll start seeing interlayer mixing and things like that. And so, not only has Peak been able to make these scientific advancements in raw materials relevant to this fusion supply chain, but we're actually able to make it at the necessary scale for the fusion supply chain. And so here I'm just showing batch of film rolls that we produced over the last couple of years, which is easily able to make hundreds of thousands of capacitors. I'm not saying we're replacing every BOP capacitor today, but we're working very, very diligently to continuously scale up our manufacturing to meet the kind of demands that we're seeing in the market space right now. And so with all this technology, Peak Nano, I think, is really making material that can greatly improve the quality and lifetime of capacitors, particularly, again, for the high current needs that you're seeing in the fusion community right now. And so while our obvious customers are capacitor manufacturers, since we make the raw film, these capacitor manufacturers will then take their capacitor, sell it to someone building a power module or some capacitor bank, and then that system is actually what you'll end up buying as the end user of a fusion company, maybe. So at the end of the day, Peak Nano is pretty far down the supply chain, admittedly. And so from a pure fusion perspective, this is kind of a tricky situation for us. We're obviously highly invested in the progress and outcome of every company because, yes, we believe in fusion as the holy grail of energy generation like everyone else here, but also because if it works, fusion companies will need a lot of capacitors, which means a lot of film sales for us. It's kind of generally beneficial to make sales. And so I say all that, it's also difficult to be invested in the fusion community when we're so far down the supply chain because we know that we can't directly engage with fusion companies to co-develop. And so if I want to know what the current limitations are of a power system or any limitations that you guys are having, It's just intrinsically difficult to join the conversation because there isn't a direct line of communication through that engineering pathway. And so we really have to work upwards through the supply chain, but you see a lot of capacitor manufacturers don't have the knowledge of the fusion supply chain. And so it's hard for them to figure out what are the necessary innovations over time. Now I say this, luckily Peak Nano isn't solely dependent on fusion. By being diversified in applications, which I think is core for every supply chain company, and being able to leverage our materials across multiple domain spaces, we can continue to push forward on the main technology and be here really to support fusion in any way necessary. However, I also know that this isn't the case for more niche solutions that may greatly advantage from the fusion supply chain in particular. And so I feel this need to continuously preach the message of trying to close this gap between fusion companies and fusion suppliers, and really encouraging the much needed conversations on current technology gaps and other potential technological solutions that would be able to move fusion faster. And so with that, I think I capped out on my time here. Thank you all, and looking forward to the panel later.
Thank you, John. Next up, we're going to hear from Brian from Thea Energy.
Hi, my name is Brian Berzin, and I'm co-founder and CEO of Thea Energy. Thea Energy is a fusion technology company building an economical and scalable system architecture utilizing arrays of mass manufacturable magnets and dynamic software controls. Our flavor of fusion technology is called the Stellarator, and we've reinvented it to leverage these programmable magnet arrays. The result is a more practical form of commercial fusion energy that can be deployed at scale. Thea Energy as a company is about 3 years old. We spun the company out of the legendary Princeton Plasma Physics Laboratory, where the Stellarator was actually first invented, and I'll get more into that shortly. Today we're about 70 employees, as you can see in the labs behind me, where we manufacture, design, test these magnets all in-house and build them to fusion relevant scale. The Stellarator is a form of magnetic confinement fusion energy. The Stellarator and the tokamak are probably the two of the most studied forms of magnetic confinement fusion energy, where we utilize large electromagnets, in our case superconducting magnets, to confine a plasma in a very specific configuration. A plasma is a fusion fuel. So within these toroidally shaped devices, where the plasma is kind of connected in a toroidal configuration, these electromagnets confine it in a very specific configuration. The difference between the tokamak and the Stellarator is really this twist in the magnetic field. Or a tokamak, every slice is symmetrical, and therefore it's a lot easier to build. The Stellarator looks like this French crawler. And by putting that twist into the system into the plasma, you actually are creating a magnetostatic, a steady state configuration. And that, and this is prior to even Thea Energy being founded, that's always been a real advantage, and one of the reasons why the Stellarator has always been seen as a leading approach to a power plant architecture. Because in a power plant, the goal is to create energy continuously, not just for a fraction of a second. You want to put energy on the grid to utilize 24/7. So that steady state nature of the Stellarator and its high efficiency are some of the reasons why it's become one of the main focuses of fusion research across the world. Unfortunately, building a device that looks like that specific twisted configuration is very difficult. And over the past couple of decades, there have been multiple large-scale integrated Stellarators, and the usual result of the system complexity and precision are cost overruns and schedule overruns. And this is a pretty universal rule here, that complexity and precision in hardware is just very expensive and very time consuming. And for reference, this is a picture of W7X during its construction. You can see a couple of people in the background that are working on the device. That really puts into perspective the scale of these superconducting magnets in the middle. So for fusion devices, for Thea and other Stellarator approaches, these are multiple meters tall superconducting magnets. And if they're 3D, if they're that twisty shape, even though they're 2 meters tall, they have to be within millimeters of precision. That's just very expensive and very time consuming. And so A number of these devices that were built went 10 years behind schedule, billions of dollars over budget. And while that's allowed for a first-of-a-kind scientific research project, if you're building a power plant based on these technologies and the result is billions of dollars of cost overrun in a decade of schedule overrun, that's not a very good product. So the foundational concept behind Thea Energy is how can we eliminate from hardware precision and complexity? And to be clear, we're not proposing any magic bullet here. We are not eliminating precision and complexity outright, but what we are doing is we're transferring it from hardware to software. So within our architecture, we utilize an array of about 400 planar superconducting magnets. These magnets, and this is a 3D printed plastic version of one from our first generation. These are smaller, wound in tension around a bobbin. These are one of the more simpler forms of electromagnets out there. And within the array of about 400 magnets, every single magnet is actually identical. They're all the same. So they can all be mass produced via simple means. And then the special part is the software control stack. This is no different than how radar systems work or cell phone towers. It's called a phased array. So we, within our software stack, are able to control every single magnet independently, just like the pixels in your computer screen right now. So every pixel is the same, but they're dynamically tuned so that you can see really complex, really high resolution images, even though the hardware is all the same. So within our array of about 400 magnets, we utilize a very complicated software stack to individually control every single magnet to make the very complicated, very precise magnetic fields required for this stellarator system architecture. And over the past year and a half within our walls at Thea Energy, we have actually built and operated what is now the world's first array of superconducting, high temperature superconducting magnets. And so this array, dubbed Canis, operating in a room behind me right now, was instrumental to us to verify the performance and show that we can create these very complicated magnetic fields, but with simple hardware. So we did that earlier this year in 2025. And from there, we actually continued the testing and operation of this device to show the practicality of this simple hardware, complicated software that's dynamic. And you can probably see it from this image on the left-hand side of the screen. Every single magnet has dozens of sensors within it. So we can tell voltage, current, magnetic field, temperature, just across many points within the array. And from that, we've trained what I'll refer to as a closed loop control system. And actually earlier this year, we published the results of this as well. And that has now actually been peer-reviewed and released just over the past couple of weeks. So we're excited to talk about this, not just in a press release format, but to actually provide our peers with the data, with the support to show why this is such a big deal. Following that, over the recent few months, we have been purposefully throwing curveballs at this array because we are really only now starting to understand the capabilities of a dynamic software stack. And so within the array, you can see a picture on the left-hand side of the screen, we have actually mismounted a magnet by over a centimeter. So that's about an order of magnitude more hardware defect than a modular coil stellarator can tolerate. And within the array, we mismounted the magnet, we mismanufactured it, we put it back in. We didn't actually tell the control systems what we did. But because there are so many data sensors and instrumentation in there, that the software stack knows exactly what's happening. So in the array and the software, that magnet gets slightly turned down and the magnets around it are turned up slightly. And when we verify the magnetic field via some very specific Hall probes, they're virtually indistinguishable, even though there's a massive hardware defect. That is a practicality that I think is really important and new to the stellarator that is now enabled by this architecture. Over the past couple of decades, I think the world and the research programs from which we spun out were very much focused on proving out the science to show that fusion is possible via these architectures. Where I think we are transitioning to now, and where the industry needs to focus on next, is how you commercialize that in a practical format. So when you build a power plant, I think it's a safe bet to believe that on occasion things are going to be slightly mismanufactured or mismounted. That's just the reality of the world. If you don't have to manufacture every single piece of hardware to 0.001 millimeter precision, you can use more standard manufacturing processes. You'll have more efficient processes as well, and more economical. So that's only one part, the construction and manufacture of a power plant system. What happens then over a period of a few decades is that systems will have wear and tear. This is no different from any other type of thermal power plant out there, to the cars we drive, to the aircraft that we fly in. Over operating lifetimes, you have parts wear out. You have things that need replacement. Most of fusion right now is focused on perfect lab environment conditions to make fusion happen for a fraction of a second. We at Thea are really trying to focus on what happens when magnets or other system structures wear over time. And that's something that allows us to have a system architecture that can self-tune, that can dynamically change parameters as this happens over the course of days to months to years. And therefore, you'll have a device that continues to run at a higher capacity factor with a lower O&M maintenance cost. That is the practicality that we're really, really focused on. Another major advantage that we've really just started to uncover here is by having a software layer that touches all parts of the system and can tune things. We now have an architecture that over time we can actually provide the system with updates. So there are parts of this world, especially for fusion research and plasma physics, that we're continually advancing, and we're continually getting better at it. Turbulence modeling and suppression is one of those areas. So we, over the next 5 and even 10 years and beyond, we will continue to have better models and simulation tools for understanding turbulence, and ultimately to making lower turbulence in your device. And for most other fusion architectures, this is something that if you learn something new, you redesign the system and the next one is better. But this one is kind of stuck where it is forever. With this architecture, with this phased array approach to the Stellarator, we have an advantage to provide the system with a software update, a control system update, and therefore actually have higher performance even though the fixed hardware is the same. So this is something that enables continual improvement of a fixed asset rather than just, oh, we can learn and do better for the next machine. So I've spent a couple of minutes here talking about the advancements and the results to date with our hardware. I want to talk a little bit about where we're going and the path to actually commercialize this technology. So we're getting really good at manufacturing these superconducting magnets. We're scaling up production. We've built the control systems that we need. The next step for us is to build an integrated system based on our technology. This device, which we call EOS, will use our planar coil system architecture to create a decent high triple product, and also do so in steady state, as pretty uniquely only the Stellarator can do. So this device is our proof of concept that not only shows an integrated system fusion performance, but just as importantly is a 70% linear scale of a power plant, so a large scale system that allows us to do all this systems integration, procurement, and engineering of a power plant scale device. So science, really important to fusion. Technology and engineering, really important to fusion. A lot of the practicality of operating utility scale power plants comes with the execution and buy down of programmatic risk of actually constructing the device and the facility. So this upcoming project, which we plan to have operational around the end of the decade, allows us to go one step further than just system technology development and scientific verification. It allows us to buy down the programmatic and execution-based risks of a power plant scale asset. So this device for us, we're going to be nearing about the 10% design completion later this year. at which point in 2026, next year, we will actually choose a site as to where to build this. So some really exciting stuff coming up for Thea Energy. And by designing, constructing, and operating that device, we have a really clear path to how we commercialize the technology and its final architecture, a power plant. So this device will be a scale-up of EOS. It will also change the fuel mixture. EOS will be a DD fusion device. It will be a subscale. We are going to be working towards a DT fusion power plant. And by changing the fuel mixture to DT, scaling up, we will have a very efficient system in terms of its ability to create on-the-grid electricity. And so double-clicking in on that one for a second, within the various fusion architectures being proposed now, a lot of people are thinking about Q greater than 1 on a scientific basis. The advantage of the stellarator that we're really focused on commercializing is back to the beginning of this conversation, relating to the steady state nature of that plasma. And this, what is on the screen now, this was actually a study done in about 2012 that looked at a number of power plant architectures for fusion. And it sized them based on a very similar magnetic field at the coil. And one thing that was apparent via this peer-reviewed study was that even if you make a tremendous amount of fusion energy, there's always an amount of it that has to be recirculated into the device. And so the stellarator shines because in a stellarator you can reach this point of ignition. Ignition is a self-heating plasma where you get to turn off a lot of the energy recirculation. And that allows you to have an architecture that creates a lot of energy, and then you can put that energy on the grid rather than having to pump it back into the device to restart a reaction, to squish a plasma. There are a number of different ways of how you would potentially want to recirculate energy and inertial confinement and other forms of magnetic confinement. But for the stellarator, it's a complicated system with that very specific French crawler shape. But if you can make that device, you can create a highly efficient power plant architecture where most of the energy created then can be utilized for the real goal, to create electricity, to put energy onto the grid. So we're really excited that the path to commercialize the stellarator from building an integrated system, because it is steady state, scales from an economics perspective very nicely to a power plant. So I hope you learned a little bit more about what we're working on at Thea Energy and why we're really excited to commercialize our planar coil stellarator technology. Looking forward to continuing the discussion here later today as part of the Q&A. Thanks again. Bye now. Hi.
Thank you, Brian. Next up, we're going to be hearing from Will, coming to us from Pacific Fusion.
I'm Will Regan, president and co-founder of Pacific Fusion, and I'm here today to tell you about our plans to develop affordable power using pulsar-driven inertial fusion with net facility energy gain by 2030 and the first power generation by the mid-2030s. There were three major breakthroughs that happened in 2022 that really transformed the fusion landscape. First, as I'm sure you've all heard, the National Ignition Facility used lasers to drive the first controlled fusion ignition, achieving the physical conditions needed for commercially relevant fusion. However, since the NIF's lasers are less than 1% efficient, we still need a more energy efficient way to access these physical conditions. Fortunately, at the same time, Sandia's Z facility reported record-setting pulsar-driven inertial fusion results using a much more energy efficient path to get to ignition than lasers. By driving their maglev concept with a pulsed electrical current, Sandia achieved the second highest fusion performance ever, second only to laser fusion. And this maglev approach has the added benefit of using lower complexity targets, which will further ease the path to commercial power. And last, that same year, the team at Lawrence Livermore National Laboratories, led by our now CTO, Keith Lachine, demonstrated an even more energy efficient and mass manufacturable pulse power technology than what's used on the Z facility. This new pulse power technology is called an impedance match March generator, or IMG, and this opens up a path to build practical and cost-effective fusion machines. So when you take these three things together, it showed that we can achieve conditions needed for commercial performance, that we can get there energy efficiently, and last, that we can do so with affordable mass manufacturable hardware. So we founded Pacific Fusion in the summer of 2023, building on all these breakthroughs with the goal to demonstrate net facility energy gain, so more fusion energy output than we initially store in the system by 2030, with a path to extend that to the first commercial power by the mid-2030s. In the 2 years since our founding, we've grown the team to over 110 staff and have raised over $900 million in a tranche Series A, where the funding is called as we achieve predefined milestones. In order to achieve these ambitious timelines and milestones, we need to bring together the world's leading fusion researchers with the best engineers and operators coming from hard tech industries. And we've been really fortunate to assemble just such a dream team with folks like Alex Zylstra and Nathan Mizan coming from Lawrence Livermore National Laboratory. They're heading up our experiments and target design teams, respectively. We've got folks like CFS vacuum group lead, former CFS vacuum group lead Fabio Ravelli, who's heading up our vacuum system development. We've also got scientists joining us from other industries like Indrani Bhattacharya, who's joining us from the materials industry, working at companies like Scylla and Corning, and she's helping us develop advanced components. And lastly, we've got a lot of great leaders coming from the automotive and aerospace industries, people like Courtney Richardson, who formerly headed up Tesla's Fremont manufacturing infrastructure, and Craig Companion, who recently joined us from Blue Origin, where he led supply chain and additive manufacturing. We're planning on growing the team even more over the next year and a half, and have about 30 openings on our website right now. So I strongly encourage all of you great scientists, engineers, and operators out there, please do reach out, check out these open roles. So with this team and these resources, here's what we're designing and building over the coming years. This is our demonstration system. We'll use this to demonstrate net facility energy gain by 2030. In short, it's a big capacitor bank that's used to deliver an electrical current pulse that rapidly squeezes a small fuel container called the target. This system is about 300 foot across, stores about 80 megajoules of energy, and can deliver over 10% of that stored energy to the target, resulting in ignition and net facility gain. So for us, more than 80 megajoules of fusion output. If we compare this to facilities like the NIF, our demonstration system only stores about a quarter of the initial energy, costs about a tenth as much to build, but we can drive targets to roughly 100x the facility level energy gain of the NIF. So if you look at that overall, it's roughly 1,000x increase in performance per cost. And if you compare us to other major facilities like Z, we can drive over 2x more current through our targets, over 60 mega amps compared to Z's 25 mega amps of peak current. And that's important for us to get the conditions needed to get not just ignition, but facility gain, high gain. So here's how the system works. Effectively 3 steps. Step number 1, you charge up your capacitor banks while you load a fuel container in the central fusion chamber at the center of the machine. Step 2 is you discharge those capacitor banks, sending a large electrical current pulse traveling inward along these transmission lines, these wires. And then third, you direct that electrical current to a tiny fuel container, our target, that holds a few milligrams of DT fuel inside. And that electrical current creates a very strong magnetic field that rapidly implodes that can and squeezes the fuel up to fusion ignition conditions and high gain. In our demo system, we'll be taking only about 1 shot a day and measuring all the output with a sophisticated suite of diagnostics. You can read about some of those diagnostics in our AMPS paper, affordable, maintainable, practical, scalable. It's our technical roadmap we shared on the archive a few months ago and is coming out in a peer-reviewed journal shortly. In a power plant, though, we'd be harnessing that output and using the neutrons to breed more tritium in a blanket. Okay, so I've showed you what we're building to achieve net facility gain by 2030. What else do we need to make power by the mid-2030s? So we actually we'll need to build a new system that looks pretty similar to the demo system. Same footprint, roughly about the same amount of stored energy. The main difference in this new system is that it has to cycle not just once a day, but about once every second or a few seconds. We'll also need to capture that energy output to generate electricity and siphon off a small fraction of that generated electricity to recharge the pulsar and to power other systems. And then finally, we'll need to close all of the material loops. So after every cycle, every target we fire, we'll need to capture and recycle all of the unburnt fuel. We'll need to capture and recycle all of the non-fuel target materials, and we'll need to process the blanket that's catching all the neutrons and bringing tritium and capturing the heat. So as we drive toward facility gain on the demo system, we're ramping up development basically across all of these areas in parallel. And we can't just be content to build one power plant that works. That's not the goal. The goal is to build machines that deliver the world's most affordable firm power. And to do that, we need to be constantly improving, simplifying, eliminating components, accelerating production of every single piece of our system to ensure that it's affordable, mass manufacturable, and maintainable as possible. Our IMG pulse power architecture already lends itself pretty well to these challenges. It's built in a very modular fashion, starting with a small unit called a brick, made up of 2 capacitors and a switch. Those capacitors are about the size of a lunchbox, so that's a pretty small unit. You then take about 10 of those bricks and attach them to a common anode ring that forms what's called a stage. And then you add up a bunch of those stages in series to form a module about the size of a shipping container. And the majority of our system is just carbon copies of that module, about 156 in our demo system, similar amount in the future power plant. So that lends itself well to mass manufacturing and scale deployment. Certain supply chains do still need to be scaled up, things like fast pulse capacitors, but nearly all of our system is built from low complexity parts and widely available materials, things like metal, plastic, oil, and water that you can source pretty much everywhere. So that helps keep our capex down. On the OpEx side, O&M costs, we're designing all parts of our system for easy serviceability and long life. And finally, to keep the fuel costs low, we're specifically developing our targets so that they have a path to low-cost mass manufacturing. And this is thanks in part to their cylindrical geometry and fairly low complexity compared to other inertial fusion targets. So we'll share lots in the years ahead, but here's what's most imminent. Like I mentioned, we recently released our detailed technical roadmap. This describes our path to affordable, maintainable, practical, scalable fusion, or AMPS. That's available now in the archive, like I mentioned, and is soon coming out in a peer-reviewed journal. We also recently completed our first set of major milestones that unlocked our next tranche of capital in our Series A, and we're using that to rapidly build toward our first full-scale IMG module. Last, I'll mention we're in the final rounds of site selection for where we'll build our demonstration system. We've narrowed it down to 2 sites in California, Alameda, which is pictured here in a render, and also Livermore, and 1 site in New Mexico in the Albuquerque area. So at Pacific Fusion, we always aim to make the fastest progress that's physically possible. So in that spirit, I yield my last 10.5 minutes, and I really look forward to your questions in the live session. Thank you.
Thank you, Will. Next up, we're going to hear from Dr. Elaine, coming to us from the ITER organization.
Good morning. This is my real pleasure to be this morning in front of you and to contribute to this very important workshop concerning the 10-year shot clock vision to a fusion energy production, or maybe at least a big progress of fusion developments by 2035. So clearly, this topic is of importance for the entire community, and I'm here to witness, in a sense, the opinion or the position of the ITER project in this respect. I will try to discuss what are the challenges that we see here from ITER and what are the kind of solutions that we can elaborate all together. My name is Alain Bécoulet. I'm the head of the Science and Integration Department here in ITER. I'm the chief scientist and in charge of both the science development, the research plan, but also the entire configuration and the maintenance of the requirements all along the development of this project. The outline of this talk is the following. So after a very short introduction, I will try to give our opinion of the landscape of the remaining R&D challenges that we have in front of us between now and the moment we can produce energy with fusion, and give some ITER considerations and contribution to this effort and the way forward. So as a very, very short introduction, of course, we all know here, and that's the reason why we are here, that we have to face an energy growth a problem or energy growth aspect in front of, in a climate constrained world. The energy demand is rising as our economies grow, as our populations are growing, and strive to improve their living standards. The sustainable growth of the planet requires for sure choices in energy, and if possible smart choices, ensuring that increased consumption doesn't come at the cost of environmental degradation or further environmental degradation. Protecting natural resources and ecosystems is a foundation for sure for the long-term prosperity, well-being, and resilience. And one of the key to this aspect is certainly innovation, but also efficiency, circular economy models to reconcile the growth or to, let's say, contain the environmental impact on this development. Fusion is one of the elements for the answer here. Fusion is transitioning now from the lab bench to the factory floor. This is the big news, and this is the reason why we are here. I've just illustrated with the TRL or the technology maturity levels of such a development. Clearly, fusion is moving beyond the experimental science now with technologies that are being engineered for much more real-world applications, scalability. ITER that I'm representing here is being built and tested exactly for this and is marking the shift from the academic proof of concept to the industrial demonstration. We are just in the middle of this scale, just transiting from the labs to industry. Private and public sector are investing heavily. We have seen that in the past almost 10 years now, aiming to commercialize fusion within the next decade or decades, let's say, through advanced manufacturing and supply chain development. The focus is expanding indeed nowadays from physics to engineering, also including progressively the commercial aspect, the grid integration, regulatory frameworks, workforce readiness, and so on. So all this is in movement now for almost a decade and is accelerating. And clearly, this is an extremely important fact of our development and our community. To discuss the landscape of the remaining challenges, I want to refer to something that was developed under the auspices of the IAEA last year. Many of us contributed, including the US DOE, including several of the private sector initiatives, and the FIA, for instance, was part of this development. And the IAEA edited a document that is called the Fusion Key Element that was endorsed by the World Fusion Energy Group, launched by DG Grossi last year. This document is not a roadmap. This document is a strategy, a shared vision for the fusion energy development, and is really covering a large number of aspects in a very condensed document. So I encourage people who didn't read this document to go to and have a look. In this document, as I said, there are many elements. I have extracted a number of elements concerning the remaining challenges. So first of all, there is a list. We have selected in this document, among a number, some really burning, I would say, R&D challenges in terms of engineering. They are listed here. I'm sure that nobody will be surprised by this, but the first in this list, the first one is clearly the materials that have to be now resilient to extreme conditions and long pulse operations. So for DT fusion, of course, we need to have elements that are resisting the high energy neutron fluxes, but in any case, also harsh thermal radiation vacuum environments, while preserving, this is extremely important for the performance, the plasma purity. For DT fusion, again, there is also the question of the fuel cycle. Everybody knows that we have not in hand today a validated DT fusion technology, and we need to continue developing this, proving, validating this kind of techniques. The power exhaust management is extremely important. We have to handle plasma heat and particle exhaust through advanced materials, advanced cooling solutions and design. This is not finished by far. We need to have much more R&D in this domain. Obviously, when this machine work and are activated, they need remote handling for maintenance. They need globally maintenance schemes, but they need in particular remote handling for maintenance. And we need to keep on developing reliable designs, remote handling systems for safe, efficient maintenance. In commercial fusion plants, this is also to be connected from the very beginning to the design of this kind of facilities in order to help to allow for an easy maintenance. And last but not least, the heat extraction is also identified. The high blanket temperatures boost the plant efficiency and require advanced reduced activation steels to ensure durability and cost-effective power generation. So you see that all these R&D challenges are at the border of what happened in the labs for the pure fundamental demonstration to what needs to be now developed and secured for the industrialization and the commercialization. I have identified a little bit more here what I call some others remaining R&D challenge. We are more on different aspects here. First of all, of course, the physics aspect. We need to investigate very clearly and more in depth and in real conditions the physics of the burning plasma, transport, instability, and so on. Overcoming Q equal whatever 5 or something, 5 to 10, let us enter into the world where the alpha particle will drive really the game, will dominate the plasma heating, so and the plasma later on behavior, instabilities and whatever. So we absolutely need to enter into this world and look, have a clear look, not only a theoretical look at what's happening. The second real challenge here is the long pulse operation. ITER will come back to that. ITER will overcome a couple of hundreds of seconds when the thermal equilibrium between the plasma and the machine is reached, let's say, or at least is approached. This raises all the problem of how to manage power exhaust and energy exhaust in a sense on very, very long terms. We are at the border of 10 to 20 megawatt per square meter in steady state in the diverter. We have to investigate the harms, the disruption, avoidance, etc. The fuel balance in steady state is also an issue, or at least a question in the plasma. The maintenance of the fuel purity also, so how we collect, we skim the plasma, we collect the DT, helium impurity gases, how we manage this, how we repurify. So all this question of the tritium plant in particular is extremely important to demonstrate and to validate. 100% actively cooling of all what is looking at the plasma. Would it be looking at directly or indirectly? So all the active and passive plasma facing components have to be validated and demonstrated that they can work in 100% stable in a sense. And last but not least, the plasma and then the overall plant control system have to operate reliably and confidently at all times under all circumstances for days, months, years, and so on. So this is something that deserves a lot of further R&D and testing. When I go a little bit further into the plant itself or into the industrialization and commercialization, of course, you face the RAMI aspects. The extreme conditions and long operation lifetimes demand robust engineering to ensure safety, performance, and cost effectiveness. Nowadays, we have to invent the design of fusion devices that are embedding the RAMI aspect from the very beginning. Of course, the nuclear safety, qualification of components, of processes, and so on, versus the regulation or the regulations, depending on where you want to sit these kind of devices. And last but not least, we have contaminated and activated, or at least activated devices that we are creating here, and we need to create the full chain of values and or the full life cycle of this kind of devices, including the waste management. A question that is bothering us and our Director General for quite some time, and you certainly are sensitive to that, is the question of the cost of this kind of devices. Clearly, a machine like ITER is setting a standard in the cost, which is very high. Can we make it cheaper? And is it by making it smaller that we can make it cheaper? So this is this kind of short discussion that I want to enter in here. I forget about the way I did it, forget about the details, the 0.08 things and others. It's not the point here. You can twist all the scaling laws and so on one way or the other at constant beta n, at a given safety factor, constant Greenwald fraction, etc., etc. You have several ways of manipulating both the Q factor and the fusion power flux to the scrape-off layer. But one way or the other, the result is the same and is a sort of stubborn result. The figure of merit really scales like basically B and R to the same kind of power. So you can gain a lot in the major radius if you gain a lot in the magnetic field. So doubling the magnetic field is certainly a good idea to start with, to make machines smaller. But as I said, the physics is stubborn here, and if you go this way, if you reduce, if you try to have machines that are smaller in size, you immediately face the fact that fusion power is produced in a volumetric way, but is exhausted in a surfacic way. So you immediately face the problem that you increase, by reducing the major radius, you increase the flux to the plasma-facing components, to the edge, by a factor that can vary again, but that it is important to keep in mind. Which means that if you double the magnetic field, which enables you at a given fusion game to gain on the major radius by a factor of typically 2 or an equivalent factor, this comes at a cost, and the cost is a significant increase with the scaling laws I have exhibited here, but we can discuss for hours on that. The cost will go by a factor of 3, 5, or maybe higher in the power exhaust density. This is critical, of course, because if we can cope with power, we can't cope with energy. In terms of steady-state operation of fusion devices, this element will directly affect the thermal and mechanical stress on the plasma-facing components and the design of the cooling system. So we don't know today how to overcome, how to go, technologically speaking, above 10 to 20 megawatt per square meter, which is the kind of power fluxes that we face on the divertor of the machine. So it is extremely important if we want to go to smaller size machines, we have to also to face significant R&D in the plasma-facing component materials. Make it the other way around. We believe very strongly that reducing the cost of fusion plants is a must, but it must come largely from the systematical optimization of the design, construction, assembly. More magnetic field obviously open more operational margins first, and we have to include all the RAMI consideration and so on and so on, rather than simply relying on downsizing the device for the device. We also are conscious, I will come to that the ITER example shows that a plant around a fusion machine is a significant amount of the capital cost. So if you reduce too much the size of the machine, you don't reduce so much the cost of the overall plant. Turning to ITER contribution more rapidly now, clearly ITER is there and has been invented and decided there to demonstrate the scientific technical feasibility of fusion as an energy source with the technologies that were available at the time we designed this machine. It targets Q equal 10 in DT plasma, a steady state operation, as I said, so pulses that are above 400 seconds, which mark this thermal equilibrium up to 1 hour or something, repetitively, of course. ITER is there to embark the entire nuclear case, the licensing, maintenance, deactivation, decommissioning, waste management in a framework which is the French nuclear facility framework, but adjusting, developing, and validating a fusion case of this kind of licensing. We are there also to prove some concepts of tritium production with different technologies. And I'll come back to that. We are here to develop and manage and transfer the knowledge and the know-how to the future actors and reactors, of course. I'll come back on that a little bit later. Along the V cycle of a big project like this, I just want to emphasize a couple of elements. So along the conceptual part and design part, we have now for many years a fully integrated design that we are of course adjusting, correcting, influencing. This design goes with a fully coordinated and consolidated research plan that is developed and validated by the entire fusion community. And as I said, the nuclear safety case that is starting from the fission nuclear case of the French regulator, and that is progressively being adjusted, cleared, or adapted to what we need. Concerning the phase of that we are in now of implementation, of construction, assembly, and so on, as you know, we have reinforced recently the project management, and in any case, we have an integrated project management in a very, very complex organization. We are coordinating 7 domestic agencies who are in connection together with us with thousands of industries. So this is a big endeavor. This is a prototyping also, but it's important to understand that it is an extremely important endeavor that suscitates the development of a number of industrial actors. So it is it is a supply to ITER. It's not yet a supply chain, but it is really encouraging the development of a fusion supply chain by doing this. Safety, quality control. So all along the integration, the test, and so on, we have been developing, and we are further improving our safety and quality control. So we are also here developing as much as we can standards for fusion, which are to be really tested, adapted, and validated. And last but not least, we are consolidating, and the ambition is to standardize the integrated modeling, the operation training, and so on, in order that ITER not only delivers fuel 10 plasma, but delivers a full framework for fusion development. So all this is covered nowadays. Every day, every single day, ITER is producing knowledge, technology, and know-how. We are working on standards, golden standards, of course, industrial ones. And I'll come back to that. We are now putting an overlayer of all this with digitalization and AI assistance. Where are we now? The ITER plant is largely constructed and undergoing commissioning. Its commissioning. The ITER tokamak is currently being assembled. I invite those who have not yet visited to come and see. This is very spectacular these days. And in particular, as you can see on the picture on the right, we have started really at a reasonable speed, if not a large speed, the assembly of the 9 subsectors of the machine, where you can see 2 already in place in this device. We have experienced some delays, in particular associated with difficulties to build, simply to manufacture this kind of big components, particularly the vacuum vessel. The dates that we have now have been readjusted after the sequence of the delays created 2 years ago by this manufacturing problem plus other ones. The start of the integration commissioning of the machine is planned now in 2033, with the start of research operation immediately after 2034, the transition to full magnetic energy in 36, and to DT operation around 39. I'm happy and proud to announce that for the past 1.5 years now, we are exactly following our schedule index, and even at a better cost index than the one. Recently, we have also mutated the ITER facility and adjusted this facility and this team to the world that is developing. And in particular, we have engaged into a so-called ITER private sector fusion project, which motto is we can go so much faster together. So we are inviting you guys, we are inviting the entire community, magnetic, non-magnetic, private, public, whatever actors. In May 24, we hosted the first meeting with 350 participants that we repeated a year after. So we already have connected with a very large number of you. And we are opening all the channels of our knowledge, the design manual, the access to all the documents that can be accessed. We have almost finished the opening of the integrated modeling suite of ITER codes in full open source. We are establishing bilateral agreements with whoever wants. We are opening our catalogs. We are organizing technical visits and so on. So the list is long. We have given access to the ITPA to private sector, and we are even opening the ITPA to some engineering topics as well. You have the email of the dedicated help desk here. If you want to connect, if you want to work with us, this is open to everyone. Last element, we are, as I said, developing or considering to accelerate and to improve the reliability, availability, efficiency of what we are doing with artificial intelligence. So in very short, we have now developed a strategy that we are submitting this fall to our members, to the council, concerning a very broad development, so in particular of AI, on all the processes, system engineering processes, the project construction, the quality, the corporate functions, preparation of the operation, maintenance, etc., exploring the frontiers of plasma science together with the fusion community, and developing tools for better training, education, knowledge, and know-how transfer in order that ITER is daily accessible to all the community in terms of what we know and what we are developing. So my last slide is here a very important message that I convey on behalf of our Director General as well. We really applaud the fact that the energy and the investments that are put nowadays in fusion are really increasing a lot. This is extremely important. We are happy to see that what we have been altogether developing for decades now becomes a reality, or is at the door of becoming a reality. To be honest, I think I told you that we need to pay attention there. It's very difficult to reach energy production by 2035 or by simply deriving smaller reactors. It's extremely important that we keep on being transparent, honest, and face the reality. But clearly, we have no choice if we want to accelerate the process, and we need to develop and to better collaborate. This is our best accelerator. We have challenges, as I said, but these challenges in a project-oriented approach is nothing but milestones, momentum, and deliverables. ITER is ready to play its part here, and I'm proud to invite you to continue liaising with ITER. We will do so reversely, and let's do it. Thank you very much.
Thank you, Dr. Elaine. Next up, we're going to hear from Oded from nT-Tao.
Okay, so I want to start by saying thank you for the Fusion Report Forum for organizing this webinar and discussion. I think it is very timely and important, and happy to be able to contribute to it. And before we start, and for those who I have not had the pleasure of meeting, my name is Oded Gourlavi, a retired Rear Admiral from the Israeli Navy, and the CEO and co-founder of nT-Tao. Our talk today is about Fusion 2035, the 10-year shot clock. Before I continue, I would like to give you a little bit about myself, a little background, and then we'll dive right in. And as you can see on the picture, I'm the guy on the left. standing behind me one of the submarines. Many years underwater, leading teams, critical missions in times of high uncertainty that required careful planning and even stronger execution. The reasons that I stayed in the IDF for 30 years was about securing the future for my children and their children. And that is the same why that I bring to this mission here on Fusion. My passion for energy started as a young submarine captain, where I had a kind of a personal connection to every electron running through the submarine. It was literally a life and death situation. Later in my career, while at Harvard, researching the relationship between global security and energy, it was clear to me that would be the biggest challenge moving forward. Energy creates everything from water to AI. And what we need as humanity is to secure abundant energy on a global scale. I started nT-Tao back in 2019 while at MIT Sloan on a new mission to harness the super innovative thinking of Israel tech to the fusion sector, standing on the shoulders of 80 years of experience and experts and knowledge, and bringing that forward to reality. Our talk today, again, is about Fusion 2035, the 10-year shot clock. There are a few challenges and opportunities that we will discuss. But before we get there, I want to briefly present nT-Tao's approach to fusion, which is a compact system, and the way we plan to beat the clock and how we do it cost effectively. So let's dive in. So nT-Tao, we're building a compact system of a 20 megawatt power supply. We believe it's going to be fast go-to-market, easy, quick maintenance, relatively easy, even for a full core replacement, easy deployment, scalable. It can connect to the grid, can be scaled to a bigger plant for the grid in a modular fashion, but can also be on a microgrid and definitely or totally off-grid. It is optimized for that kind of distributable, scalable power, which is the power ecosystem we're heading towards. We can see it mainly due to renewables that are creating the necessity for the power grid to go distributed and be more able to work in distributed modes. But also, and for a stronger reason, we need that distribution for security and redundancy, for national security and redundancy, which are very, very important. What is our differentiation, or where are we situated? This partial map has been developed over several decades. And following extensive research into the most efficient areas for fusion work, our focus has been on high energy systems driven by the need for strong power supplies, pulse power, and high density plasma. We sought the most optimized and efficient regime for fusion, which led us to recognize the need for the high density conditions. At this density, we saw an opportunity to combine the magnetic confinement technologies with the most advanced and mature heating and energy transfer systems. Those are the pulse systems on the left side. And on the right side are the magnetically confined plasma, the tokamaks, the stellarators. This combination of pulse modes and the magnetic confinement, as shown in this figure, is the most efficient approach, we believe, that is enabling a compact fusion system and actually lends itself to a smaller compact system. And so we went for this optimization for high density, higher efficiency, and the combination of the two. The figure illustrates the opportunity that we are seeking, and we believe it is the right approach. So the solution that we are building, as we said, is using the backbone of the magnetic confinement based on the stellarator design, fast heating by very, very strong pulse power and power electronic units and active stabilization fields. All of those combined enabled to be performed on this system. In the picture, what you can see is our current system on testing and experiments, C2A. That is the third system of that sort and model, and it incorporates the design and the heating and preheating systems that we have built. Over 1,600 pulses already being pulsed on this system, and creates a huge amount of data points for our next design. This solution, as we say, is incorporating all the parts together, and the engineering milestone that led us to this stage is a very rapid full prototype engineering cycle, from simulation to design to engineering, building, and eventually testing each and every part of the system as components, and eventually connecting them all together. The validated C2A backbone of Stellarator has been tested at the end of last year, and we're continuing and progressing very quickly to the next stages. The power that you can see here, those power units, those are proprietary power units that we've built in order to be able to push those magnets and to heat the plasma all together with the entire system and machines. The simulations that have been enabling us to design as part of the full prototype engineering cycle are based on simulation codes from Princeton, the Desk One, the Strufi with the MHD from Max Planck, and other MHD and gyrokinetic kind of simulations and more. Those are all incorporated in the process of design. We're adding top-notch diagnostics that we've built in collaboration with the top institutes in Israel and abroad. And those are all incorporated in order to really get all the information through those experiments that we're doing. And we also are building HGS magnets that are specifically designed to be able to work in very high pulses. So those HGS magnets will be tested, they're already built and will be tested in a pulsed environment very, very soon. So let's go now, after looking at nT-Tao and our approach and general approach, and a little bit about technology, let's go and talk about the bottlenecks and what will take us to 2035. The bottlenecks, the main bottlenecks, I divide to three main vectors: the reactor challenges, the full system challenges, and the market and public challenges. And if we take a look at the reactor challenges, we all have the goal of Q greater than 1, and on the engineering side, not the scientific side. And that's a big goal for everyone to achieve, for us as well, obviously. And the next stage, and that's a big issue, is reactor to electricity path. And that's something that part of it can be in collaboration, and part of it is internal to each company. Some companies have their own special means of moving from fusion power to electricity. I believe that will be discussed as well by others. But we're taking the path of the more conventional, moving through steam or other means to run a turbine and then a generator. Tritium breeding technology, that's an essential challenge that everyone using deuterium tritium needs to resolve. Deuterium tritium is the easiest kind of fusion fuel in terms of temperature and energy, but also has the lack of tritium. So tritium breeding is essential, and that's an area for a lot of collaboration possibility in the ecosystem. Trained workforce, that's essential. And that's a big issue for this decade. When we increase space, increase the capability of the companies in order to move faster, but also achieve our goals for 2035, we need a trained workforce. And that's another challenge that we have in front of us. Another one, and the discussion on full system challenges. And that is, first of all, government investment to reduce supply chain constraints. When we discussed specific supply chains, and that can be maybe in another discussion, but government can signal suppliers that they can reduce their risk and join the ecosystem and start pushing forward in order to be ready for 2035. Some of that is mass production and distribution. especially for a compact system like we are planning, mass production is the way, which will also reduce the cost, but is also something that we need to be prepared for. So that's another challenge that we see ahead. And materials and manufacturing, that in precision manufacturing and certain materials that need to be created or developed for the plasma-facing materials, etc., and other elements in the machines, that's also an area for collaboration, and a lot of that can be done and reduce risk mutually. And then the last one bottleneck that we want to discuss is market and public challenges. First of all, more private and public investment is required for the R&D phase, but also for the reduced process of going into market and creating the first of a kind, etc. So that's part of the challenge for the public. Regulatory policy that enables us to move faster in the process of the development, but definitely to be prepared for the final market process. International regulation is also, we see some of that being created already in the IAEA, but I think we saw the NRC leading in the US in terms of regulation for fusion, making the differentiation between fission and fusion, etc. That's a very important thing, and we should see that going on a global scale as well. And regarding public awareness, that's not a small thing as well. In terms of the community preparedness, media is part of the process, and education. We are very much engaged with students and teenage high school students to come visit, learn what is fusion, get aware of where we're going, and be the next generation. Decade from now, they will be leading this process in the market and creating the new generation of fusion reactors as well. So those are the main bottlenecks that we see ahead of us. So moving on to the global leadership challenges, because most of challenges and even bottlenecks, eventually we need leadership to lead and solve. And the race is on a global scale. So what we see the need for stronger government leadership to reduce supply chain risk, we discussed that, and that's leadership, not only the process. And then common challenges are common risk, and that's an area for collaboration opportunity. We had a few challenges. One of them is the tritium breeding, the blankets that are out there, the plasma-facing materials, and other issues that are all surrounding those reactors and systems. Those are excellent areas for collaboration. I mean, if submarines and submarine forces from around the globe can collaborate on safety and rescue for submariners within submarines, while all their missions are always super secret, but on those aspects, we can collaborate, and we do on a global scale. I think we definitely can find a way to make more collaboration in the fusion ecosystem in the same manner. Also, multiple shots on target are essential. And I think the fact that we have about 50 startups, different technologies, and the more different technologies that we are pushing at, the more chance we have to get by 2035 with a full fusion capability going to market. So this is very good and very important. For that, we need the leadership in terms of funding, the government as well for that, and also to create national strategies that can push forward into that process. And enabling regulatory framework internationally and nationally, I think a very important aspect of that. We see, as I said, the NRC moving forward. We see other countries pushing as well and getting to that stage. And what I think is an important proposal that we suggest is to propose a US-led sandbox for sub-50 megawatt fusion systems, enabling fast-track approvals and global alignment. It's a proposal that the goal is to de-risk both the technology and the regulatory process at the same time, so that when 2035 arrives, fusion isn't stuck in licensing purgatory. Key features of Fusion Regulatory Sandbox could include, for example, eligibility limits, i.e. like only systems under 50 megawatts with specific safety case parameters. Streamlined approvals, meaning shorter timelines for siting, environmental review, and operational permits, and standardized safety cases, shared technical baselines for shielding, tritium handling, and operational limits, and international reciprocity. Data from one sandbox nation could be accepted by others to speed global rollout. So we believe that that's an opportunity here as well. And for a summary, and just to summarize everything, compact, we believe and think that compact is the right path. We understand the technological hurdles, but also the capabilities that enable what we want to achieve. We're quickly reducing those risks. And to get to 2035, we will need more collaboration than we see today. To get to 2035 with the market ready requires more government involvement. Fusion by 2035 isn't a hope, it's our mission. And as I used to say to my sailors, it's all hands on deck. The race is on. Thank you.
Thank you, Oded. Next, we're going to watch a short video from Helical Fusion before we get into our panel discussion.
Humankind has been seeking to emulate how the sun creates its energy since the middle of the last century. But creating the reactions in the sun down on Earth is incredibly complex. Solving it will take some groundbreaking technology. Helical Fusion is developing pioneering ways of helping achieve this goal of predictable, clean, baseload energy for the planet, and it starts with a relatively small piece of ingenuity. At its core are layers of advanced superconducting materials. Next-generation high-temperature superconductor, or HTS cables, enable stronger magnetic fields, making the reactors smaller, more powerful, and more efficient. Hundreds of these HTS cables will combine together to create groundbreaking, high-temperature, superconducting magnets. And crucially, because the HTS cables are designed to be flexible, they enable a unique geometry, a double helix, two spirals that form the very framework of the reactor. This double helix will provide an unimaginably strong magnetic cage to hold the energy source of the reactor, the plasma. The plasma will be 10 times hotter than the core of the sun, and so can't be in contact with anything. Inside the hot plasma, two hydrogen atoms, deuterium and tritium, collide to create helium, a process that carries no risk of runaway reaction. But crucially, this reaction leaves a spare neutron. And as E equals mc squared explains, this neutron carries a huge amount of energy. In order to harness the energy from the neutrons, the plasma will be surrounded by special structures called a blanket. Here, the Helical Stellarator power plant will have another piece of ingenuity that separates it from other reactors. The inside surface of the blanket will be covered in liquid metal flow. Helical Fusion is developing a system so the blanket can efficiently carry the heat out of the reactor, a liquid metal blanket. Generous space between the coils means blanket parts can be swapped quickly, enabling faster maintenance and higher plant uptime. Helical Fusion's design builds on the legacy of Japan's Large Helical Device, LHD. One of the world's most advanced stellarators, the LHD has achieved over 3,000 seconds of steady-state plasma, proving the stability of this approach. We are now bringing this proven foundation into the next generation of fusion power plants to bring clean, predictable power to the grid, helping humanity evolve through fusion energy for generations to come.
Okay, now Mike's going to take over and we're going to get started on our panel discussion.
Hey, Mike, I don't think we're picking up your audio, sir.
Yep.
Sorry, can you hear me now?
There we go.
Yes.
Okay.
Yeah, we can.
Well, I'll do that again. So thank you again to all our panelists for being part of this. Let's jump into the questions, and we can just go in the order of the presenters answering it. So the first question for the panel is, it seems that many of the supply chain areas are developing nicely. What are the greatest remaining supply chain challenges? What kind of keeps you awake that fusion energy needs to conquer successfully to reach commercialization? Why don't we start with you, Ben?
Yeah, sure. So I'll preface this by saying I'm not a procurement professional, but as we look through where we're headed next, I think enabling the suppliers who have stepped forward and helped us on things like Spark being ready to scale up to do commercial applications. So in many instances, we had suppliers who were taking their equipment and using it in a different form or function than what it was really initially designed to do to make a part or component for us. And to really scale up that manufacturing and bring down the costs associated with that, we need to move to more custom hardware fabrication. And with that, we mean a lot of capital investment into those companies. We can help that by providing them, from at least from the commercial standpoint, a roadmap of a portfolio of sites that are going to be down on the pathway. So all of that together helps ensure that they have the right needs. I think the other thing we'll be looking out for is how you think about continuity of your supply chain during the early stage of an industry. When we build our first plant, and between that period and the next plant, how can we make sure to keep the skills and workers and talents that we develop in this process gainfully reemployed towards something else related to fusion? So I think those two challenges right now, not in a single component or piece, but more of an infrastructure evaluation.
Excellent, thank you. John, I think you're next. What are your thoughts on this matter?
Yeah, I think it's similar to Ben. At least from my purview, one of the biggest issues as a whole is really like in specialized materials, components, not necessarily the full vacuum system, which I know is another issue from precision manufacturing, but things like tritium handling has been talked about a lot. All of the electronic components, so the fast switches, the volt capacitors. These are things that are on the technological horizon, but exactly like Ben kind of flagged, unless it's diversified into other markets, companies don't have a lot of incentive to scale up to where fusion will need to be in the next 10 years. And so things like the roadmap and planning and figuring out kind of all of the integrated systems now for what's needed 10 years in the future is probably very critical to help both the suppliers and fusion companies be where they need to be in 2035. So yeah, I think it's really on the materials and components scale up for manufacturing.
Brian, what are your thoughts on this as well?
Yeah, so it's a lot of things as this group has been starting to hit on. First of all, the blankets are always top of my mind, and I think they're opportunities. They're for sure work to be done, but I think they're capabilities for us to utilize things that already exist in this world for fusion. So that's what we've been spending a lot of time on at Thea.
Alan, obviously you guys have a bigger budget than most, I'll say, although it probably doesn't feel like that to you. What are your thoughts on the matter?
Yeah, so I think, as I told you in the presentation, I think fusion is a system of systems, first of all. So we have to understand that we are embarking in a process to industrialize a technology that is not fully mature and fully finalized, or with not stabilized the solution, not everywhere. So this supply chain has to continue working with the labs and with the R&D, because there is a lot of R&D to be finished, to be completed before we can imagine that we go to industrial solutions. So the very important guideline is certainly that we have to rethink from the concept, and I saw many examples which are very good here. From the concept, we have to stabilize the systems, exactly what are the systems that are mandatory and that we connect with each other. And then each system is a system of subcomponents and others, and then we can go to the supply chain. So my belief, in any case, in developing, I mean, I have some, let's say, lessons learned also from the fission industry, in particular in France, which is quite developed. I think the one way is certainly to have a couple of integrators, so really companies that are looking after doing reactors, let's say, and then that suscitate that do this job of developing the system engineering in a actual meaning, and then going to the supply chain. We are still in a transition phase for me. We are still in a system where the supply chain builds up when it now ultimately should flow down from the integrator needs. So we are approaching we are moving forward. It's wonderful, but I think we also need something like big integrators that now really intend to build hundreds of reactors in a commercial way and then drive more substantially the movement. But it will come. I'm sure it will come.
Very good. No, Oded, obviously you're a little bit on the other side of the spectrum as far as budgets go. What do you kind of see as kind of the way to move this forward?
Yeah, so I think that on the issues of supply chain and challenges that we see ahead, I totally agree with the issues of materials. There's issues of plasma-facing materials that are bothering us. We are a compact system with a high energy, very high instantaneous hitting the walls, and also average heat that needs to be dissipated. So those materials will have to suffice and make sure that we are able to do that. But also because of the compact system and the pulse power, one of the most important things is the capability of power electronics to move to the next level of high energy pulse power. Some of them maybe, some of the technology is based on diamond based or other technologies that are going in and enabling some of those very strong high energy pulses. I expect in those kind of technologies to increase their pace and hopefully make sure that we can make even smaller and better machines. But I think those, and I agree with the other panelists in that sense.
Excellent. Well, you kind of queued up the next question here, which is a lot of companies are looking at smaller fusion systems for applications like off-grid power. I know you, Oded, and especially your companies like that, but seaborne vessel propulsion and eventually spacecraft. For those who are Star Trek fans, I guess that one probably holds a lot of value. We'll start with you. What kind of unique challenges do these applications pose for fusion systems?
The challenges is those systems or those kind of applications need, and I wouldn't go as far as space very quickly, but let's start with the challenges of maritime and other systems. A large ship is very similar to what happens on land. It needs to work there as well as other places. There are benefits, by the way, in being at sea. You have water to clean, reduce the heat, to remove the heat and cool the system all the time. You are able to use it safer if you need. So there are actually benefits in that kind of element. So I think the market is actually very, very much in need for these compact systems, for the ability to put it distributed and not to rely on grid to really bring the energy where they want to build stuff. If data centers want to be built, they need to wait 10 years for the grid. Some countries have grids that or haven't been evolved or are too old, and it takes a very long time. I think these kind of systems can be put and push data centers just as an example. There are other compact and needs like island nations and industries that are further away from areas of the grid, etc. So I think there's a lot of pull from the market. So we're hoping to get that.
Ryan, what are your thoughts on the matter? Ben, what are your thoughts on that? I'm sorry.
Sorry.
You're asking who? Ben?
Ben, yes. Sorry.
Yeah, sorry.
Yeah, so I'm not prepared to talk technically on the merits on the smaller side. I do think when you look at the smaller distributed generation portfolios, you have to start thinking about whether there's a level of support that's going to be necessary for those things, sort of thing from ranging from distributed training to have you provide asset support and management for distributed architectures of things. And those are typically things with relatively small margins as you think about how to scale that up and to be able to deliver the service that would be necessary on the back end. I think the fundamental value proposition of having more compact devices and more applications makes sense, but just other commercial considerations down the line.
Excellent. Brian, since I said your name first, what are your thoughts on this?
This is one that I think there's some fundamental principle to fusion that there's just no changing. Kind of the law of thermodynamics, or one of the laws of thermodynamics, that under a certain scale, you're dealing with a really rough ratio of surface area to volume, and it's really hard to retain the heat in the plasma. On the flip side of that, the bigger you go, you have multiplications of programmatic risks, and you get to, I think, learn from a lot of stuff that's happened on fusion when you have multiple gigawatt sized facilities, the cost, the schedule components of those, the actual size of components. But I think it's incredibly important, especially where the industry is now, to be super transparent on some of the things. And I'm looking at the chat box as we pop up, like the point of fusion, and I think most of us, if not all of us here, are talking about DT fusion. That is the one that I think is commercially viable within our lifetimes. The great thing that comes with a DT fusion cycle is a 14.1 MeV neutron. A lot of energy that you then can convert, but there are requirements for blankets. There are requirements for shielding that are pretty basic and fundamental to all fusion approaches. I don't care which way you're doing it. So for Thea, and the way that we've studied this with a team of experts in neutronics and physics that think about this on a daily basis, we have a system that's a few hundred megawatts, and that's the right sizing for the energy balance for the engineering, and also crucially, blankets and other materials in the system that are a requirement. So for us and for the stellar architecture, that's a multiple 100 megawatt electric range. And I still think as this industry goes from development stage to commercialization, that will be an industry-wide trend based on thermodynamics.
Kind of finding the sweet spot in a sense now. Alex, let me tell you the question again, because thank you for joining us. So the question was, a lot of companies are looking at smaller fusion systems for applications like off-grid power, seaborne vessel propulsion, and eventually spacecraft. What unique challenges do these applications pose for fusion systems?
Got it. Well, yeah, thanks for the question and the invite. Sorry for joining late. I guess you guys started a little early. I think Brian said it well. The physics risk of most fusion approaches goes down with larger scale. The financing and execution and other risks go up. It's hard to comment in general on some of these other smaller concepts. I mean, I think the general statement you can make is, for investors, that's a higher risk, higher reward bet. There are more challenges in many ways in coming up with a very compact, portable or mobile or very distributed fusion approach. On the other hand, there's tons of commercial advantages and applications if you can do that. And you listed some of them. Part of our thesis at Xcimer is very much what I said in the beginning. The physics of inertial fusion gets easier with larger scale. And there's past data, past success, not just from the National Ignition Facility, but from decades of development at the U.S. National Labs that bear that out. So at Xcimer, we are pursuing baseload, large-scale power generation. We think the commercial market will be there for that as our electrical demands increase, not just for AI, but for transportation and all kinds of other things. So I think there's a lot of interesting commercial applications in smaller scale approaches. But inertial fusion doesn't scale to small size. So we're going to remain focused on baseload, hundreds of megawatt power plants.
John, I don't know if you want to throw in something before we go to Alan, who's definitely on the larger side of the scale. So
No, I think everyone nailed it. I would have said the exact same things. I mean, it's hard enough to put a fusion reactor on land. We're not quite ready to put on a boat quite yet. It'd be awesome. I'm all for it, but definitely some engineering challenges there.
That's that's the reason we're here.
Exactly. They exist for a reason. But
there's a reason for us to spread around the capabilities, and I think it's a good opportunity.
Alan, what are your thoughts on that?
Okay, so I don't want to repeat all what was said because I am perfectly aligned. I want just to add something. Let's not pretend that fusion can replace every single source of energy for every single application. We are not there. We are very far from that. So we are today all working in order to show that there is a new solution coming in the game, coming in the mix. So let's focus on this one, and let's see later on if we can miniaturize the systems further. I was born in France, in the very border of Switzerland, where the people are building watches. Okay, so I have this very let's say peasant approach that they started with those very big clocks, and then progressively they went down to the wrist watch. Okay, so let's do this way. Let's prove that we are right and that we can drive energy substantially out of fusion first.
Excellent. So
May I add something, Mike?
Yeah, go ahead.
Because it goes to that point. Many years ago, when Israel needed to create Iron Dome, it was said it would be impossible. It took 2.5 years and it was done. There are ways sometimes, and I'm not saying that I'm going to be able to solve, or nT-Tao is definitely going to be able to solve. I don't think anyone here knows that they're definitely going to be able to solve it, but we all have our path. But things are possible, even if you go small scale or large scale. It's in terms of determination and focus, I believe, but also I totally agree. It's a lot of science, it's a lot of engineering, a lot of hard work. And I think there's a lot of collaboration potential to make us all succeed.
Excellent. So let me start then. I'll go to you, Alan, with this next question, and we'll get you looped in as well. Thank you for joining. And the question is, how can large experimental efforts like ITER benefit fusion commercialization over the long term?
So I can start if you want. I mean, I think I demonstrated a little bit in my slides, but let's come back here. Let's be very clear. We are the fruit of what the community was pushing 20 years ago after what, let's say 4 or 5 decades of R&D, and with technologies that were available at that time, including demonstrated, like low temperature superconductors, etc. Remember that even ITER, the very first plasma-facing components were in carbon, in graphite, and this kind of things. Okay, so we have evolved also the design. And yes, we went the large size, we went the public way, and we went the totally collaborative way. So there is a price to pay in order to develop the things all together in a public approach. There is a lot of R&D that was suscitated by the ITER project. I think that the entire results of the fusion community in the past 20 years is linked to the ITER drive. Just count in your publication how many times everybody says, I'm ITER-like, I'm ITER-like. This is exactly, or ITER-relevant, this famous ITER-relevant. So this was a major drive, and it still exists. This drive exists. So we are the, let's say, I can even say the ultimate public lab, or the worldwide public lab that is there to push for the developments, for the R&D, on solutions that there is no incentive, there is no mission of ITER to be industrial, to forecast the industrial aspect. The goal of ITER is to demonstrate the feasibility, the integrated feasibility, science and technology. Yes, it's a long endeavor. Yes, it's a very large cost, so we need to work on that. But you are there. I mean, the industry is now taking off, and starting from this, to make it industrial and later on commercial. I think these are 2 steps that can also be separated. Sometimes you may have an industrial solution that is not really commercial one, and then you continue developing. So if I'm referring back to this IAEA document, the fusion key elements. you will see that in this document, there is a very clear distinction between what is now the public endeavor, the public power in fusion, making possible you guys to have platforms, to have R&D test facilities and so on, to develop, to continue developing the fundamental aspects so that you can industrialize and integrate. So it's we are in a relay race. I mean, we are really passing the knowledge and so on to the people who know how to industrialize very clearly. So that's exactly what we are doing here. That's exactly what we are doing. So it's not ITER against or ITER before or ITER after the others. It's ITER with the others continuing this. Let's say climbing of the TRL scale or whatever, call it the way you want.
Excellent. Will, let's jump to you since you haven't got a shot at a question yet. So what are your thoughts on how ITER can help commercialization fusion?
Yeah, I think Alan said it well. I think you're developing critical capabilities at places like that I think will be a broad benefit to the whole community. I know there's been some workshops recently where the ITER group has invited private companies out to be able to interact with those researchers and have more cross flow of the technology. I think workforce is critical to have a robust workforce, and projects like that also help train a generation of scientists. That's essential, and that's the same is true of U.S. national laboratories. I mean, that's where so much talent is created. Yep.
Excellent. Ben, what are your thoughts on the matter?
A lot of great points already made. I would add supply chain is an important element of this as well, especially for a company like CFS is building tokamaks, that they've been able to lay the groundwork. I think making more of that discoverable could be a benefit to what we're working on, trying to understand that better. I think the ITPA program is a great step in the right direction for the physics sharing and allowing for the exploration of more research. And I think, in general, this whole idea of the workforce, right? There's been a lot of people who have gotten a lot of experience and exposure through the opportunities created for and through ITER that otherwise at the time there wasn't anywhere for that to go. So I'm really glad that was a stopgap for a lot of people to work through this project and then to be able to then move on into the commercial sector as we continue forward. So grateful for all that for sure.
Brian, what are your thoughts on the matter?
Yeah, Ben's point is spot on. So ITER and national labs and academic institutions were working on fusion long before any of the companies on this call were around, and where I think we're at this moment where we can all learn from that hard-won knowledge. So it started to happen over the past couple of years. I really am excited to see this only continue on in this trend over the next couple of years. But some of the decisions that ITER made around what concretes to use for the biofield, those are types of information that we can benefit from, we all can benefit from as we look to build our integrated systems coming up that we're really interested in accessing to leverage.
It's good not to have to be the pioneer that gets all the arrows in your back, which unfortunately Alan and his group have had to do to some extent. Odette, let me ask you the question, then John will go to you on that.
Same question with ITER. Okay, so the question with the issue of ITER, I think it's a great body of knowledge, and I very much appreciate the opening the access to the different points and the different elements that you said, open source, opening it really up. I think it's super important, and it created really the base where we can all push forward from. I think it's a great body that can help. I agree with Ben points on the supply chain stuff. Some of what the things in ITER are relevant for us. I think one of the most important things that will be relevant for all of us is blanket testing. I don't know who will do the first blanket testing, but we will all be very, very happy to see results and move fast forward on these things. So all in all, I think it's a great to see in this kind of panel ITER with us.
That's why we invited them. So that'd be useful. John, on your last thoughts on this question?
Yeah, I agree with everything that's been said so far. I mean, I think not only is the open source model enabling a lot of kind of the next steps in the physics discoveries, but also the entire supply chain across the board. It really, ITER, buying concrete from some vendor is really setting the precedent of what every company is going to do thereafter. And, this is a conversation point that constantly pops up in supply chain meetings is, um, normalization across products. And that's something that's really lacking right now. You see in computer networking, I can buy the same Ethernet cable and it'll plug into every computer in the world. I can't do that with a fusion machine when everybody's engineering things so differently. And so starting to set some form of precedent on these very low level components really helps kind of those early supply chain companies get to the scale they need to be, again, to hit the timeline of 2035 for a lot of these reactors. And so that precedent is really critical.
So one thing, I'm going to throw in a ad hoc question. One of the things that surprised me when I first got involved in this market a couple of years ago is how much people were worried about human capital and or the lack thereof. And I heard it from everybody I talked to. If you had to tell somebody that's going into college why they should study the physics of fusion or the engineering of fusion, kind of what would your answer be? Ben, I'll start with you on that one.
Yeah, physics and engineering are a need. The workforce that scares me more is welders, and having enough welders to build and frame turbine buildings with all the other turbine buildings that are going up now. And so, I think across a broad spectrum, I think there's an incentivization that needs to be coordinated with states and with regions that we're looking at coming to that shows the potential here. I think the excitement of the industry of generating sufficient buzz to give people a reason to want to do this now from a more dedicated fusion craft. But it's the broader skill set of crafts that we're the more challenged with trying to procure on a broader scale. And then how we can then incentivize that to be in where we want it to be versus another industry. That's where I'd see the bigger race between technologies right now.
That's a really good point. It's funny because one of my sons who's in business decided to take a couple of years off from college to become a machinist for a couple of years and see what that's like. And for a skill that was supposed to go away with robots and everything 20 years ago, he said there was more work than you could ever shake a stick at. So that's a really good point. Alan, what are your thoughts on the skill issue?
Yeah, the answer is it can be very long, but the aspect that Ben mentioned is very important. There is another aspect that is important, is that fusion is really assembling the largest number of physics and technologies that ever that we can dream of. I don't think I know, after 40 years of fusion, I don't think I know a single field of fusion or engineering that is not called by fusion, that is not interested by for fusion. So it's very exciting. I mean, if you really want to do physics or technology, I mean, this is a playground that is amazing. Really one. That's one point. The point, of course, of the societal and stake is very, very important. And then I play this game because I'm here and I'm ITER. The international aspect of fusion research is amazing. For 70, 80 years now, this research has been totally international, totally collaborative. It is a wonderful diplomatic, science diplomacy aspect of fusion that we need to keep as well, because of this human stake. Yeah. We are really touching something extremely important for the future of mankind. And this is really exciting. This is really exciting.
Excellent. Brian, what are your thoughts on this matter?
Yes. Skilled trades are really important here. And they're important on every step, from how you set up an architecture to how you design, manufacture, construct, and operate. What I think we can safely understand, make as a baseline assumption, is that power plants, whatever type gets adopted for fusion, they're not going to have a capability to rely on physics PhDs to be the ones constructing them and operating them. They're just not enough. We need more physics PhDs, but ultimately we need to actually just design an architecture that works within the confines of an existing industry. The energy industry is a fairly large one. Therefore, our fusion devices need to mesh up with the industry. There's plenty of interesting things to think about in there beyond just that baseline of design. You, as seen in the United States and across the world, even if you want to, what could be seen as a a commoditized form of power generation with a combined cycle natural gas turbine for your queue. So we need more of all these things. But ultimately, we have to design an architecture that even can scale to begin with. Yeah. And I think a lot of us, if we're just thinking about pure plasma physics or first of a kind science, doesn't necessarily mean it naturally scales across the hump to commercialization. And then it doesn't mean that it scales from one first of a kind to 100 nth of a kind.
Yeah, good point. Will, what are your thoughts?
Sorry. Yeah, unmuting. Yeah, I agree with the comment that we're going to need a lot more welders and sort of technicians to actually put these systems together. I do think we've had a lot of success, and other fusion companies have as well, like bringing folks over from automotive and aerospace industries. Like a lot of our technician team comes from EV companies. I think the sort of specialization goes up roughly like 1/R as you get into the sort of chamber area. There's a lot of areas where we have to bring together fields that haven't worked together in the past, material science, nuclear engineering, thermal engineering, all of that together in the blanket chamber area. So it would be great to see, I think those skills exist in isolation. It would be great to see a little bit more multidisciplinary programs at, colleges and whatnot, to help sort of start that interaction. I mean, we can always do it in our companies, but it's great to get people up the learning curve more.
Alex, I know one of the reasons you guys placed yourselves in the Denver area was a lot of the talent that was available in that area. What are your thoughts on the matter?
Yeah, well, Denver has been great for us. Denver has a really strong aerospace and defense and manufacturing industrial base, and also a lot of optics and laser suppliers, thanks to CSU and long history of excellent programs there. I think someone else said it well. Fusion, there's not just a single domain or a single specialty that we need for fusion. I mean, almost every technical and engineering domain, way beyond just plasma physics, ultimately is what you need to put a plant on the grid. I think the way you originally phrased the question was, what would we say to someone considering their choice of major in college? Like, why would you work on fusion? And I have a really simple answer to that. I'm sure it's shared with others on the call. Fusion is the ultimate energy source, and it's inevitable that ultimately humanity is going to master energy production from fusion. We already know it works. The sun is gravitationally confined fusion. Some of you on the call may have heard my motto, which is fusion is simply solar power without the middleman. There's not going to be anything that humanity develops after fusion. It's just a question of when and how we get there. And the potential, like what inspires us at Xcimer to work on fusion, is the potential for what humanity can do when we have access to a source of energy that allows the same growth and expansion and creativity that fossil fuels did at the beginning of the Industrial Revolution. That's the pitch for why people should spend their lives, their careers, and their investment dollars, aside from the pure financial return, of course, on making fusion a reality.
I like that. Oded, what do you think? I mean, obviously you're a smaller country with more confined but very capable labor source. What are your thoughts?
Fusion excites people, and basically, first of all, from the mission and the reason and the meaning of fusion and what it will solve, I totally agree with Alex, and that excites people to go and work on it. We used to have here vocational schools. We used to have schools that taught people how to really work with their hands and how to build stuff. Today, maybe there's one. I think there's a big opportunity and need to create or return to the ability to educate many specialists in the field. But as there's faculty for law, that create lawyers. There's faculty for medicine to create doctors. There should be a faculty for fusion to create fusion people that work in fusion, and that's an opportunity that we could and push that level of study, but under colleges and high schools that can really lift out some of the population into this kind of workforce that I think is going to be the most important for energy on a global scale. So it's an opportunity as well. It's a challenge and an opportunity.
Excellent. John, we'll go to you on the supply chain. It's slightly different, but what are you seeing?
Yeah, I mean, I think it's redundant with a lot of things people are seeing. There's immense need for kind of the more labor-intensive, vocationally trained workers across the board. And I think bringing them into the fusion community is important. And I think a lot of what Alex said is really resonant there. You know, you have this holy grail source. This is humanity's last step. But, you know, I kind of want to go back to your phrasing of what do you tell the college students and try to combine answers here. I agree very strongly with Will in that like multidisciplinary studies is really what's needed. And so I actually want to tell college students, go study whatever the heck you want. See you in 5 years after you're done. Now come to fusion now that we're kind of moving forward with it. Because, you know, if everyone's trained the same way in fusion, we're going to have a bunch of people just doing, you know, theoretical nuclear physics all over again, which is important. But, you know, we need people that have thermal backgrounds, mechanical backgrounds, electrical backgrounds, and then pull them into kind of this framework. And so, yeah, I think that's kind of the multifaceted answer to this, at least from my perspective.
Great answer. One more question for the panel before we go to the Q&A session, and that is, what is the right role for governments to play in the furthering of fusion energy towards commercialization? Then we'll go back to you and let you start on this.
Yeah, I mean, we're grateful for the help we're getting. I think there's obviously opportunities to do more. I think, and broadly, you can break it down into investments of a lot of different forms. And so it could be, you know, forms of capital support, which doesn't mean direct capital, but it can mean access to capital as we move towards trying to deploy lots and lots of large assets onto the grid, and how we get the capital for those. It's going to be important. I think across research and development, there's still an opportunity to build platforms that help us accelerate the commercial aspects of this. But I think that requires governments to really orient their programs towards the commercial side of the industry now, and try to find ways to funnel avenues and priorities towards the objectives of the commercial sector. And then so that those funds are best used towards the ultimate goal of fusion, which is to provide energy that we can use. I think, you know, if we look globally and broadly, as we look at the regulatory landscape, it's emerging. We are really, I'd say, happy with what the United Kingdom and the US has done to provide the types of certainty and what we think are really appropriate regulations. So that's a template that others can follow off of and try to harmonize as much as possible to make the barriers to entry at a market as small as possible. And so I think we have really good precedent with two very credible organizations through the UKAEA and the Nuclear Regulatory Commission here in the US, and its work with the agreement states here in the United States, that can cascade. And I think taking an active role and making sure that cascades and is harmonized are all great things. And I'm sure there's lots of other things that the team here will want to chime in on. So I'll pass it to the rest of the team.
Alex, let's go to you on that, on the next one.
Yeah, I think, I mean, there's two different sides to the answer. One, for those of us on the inertial fusion side, right, there's the U.S. national labs, right, that have paved the way for much of the work being done in inertial fusion. Of course, the National Ignition Facility being the most prominent example, and continuing to emphasize the role of the labs in technology transfer and development and workforce and all the things that we discussed, you know, earlier in terms of the transition of this technology from, you know, initially a defense targeted national priority into the commercial sector. That's certainly one area. There's a really similar analogy one can draw to commercial space. And I think that's where, you know, many of us in the fusion industry are looking and hoping that the US continues to take inspiration from. The commercial crew and commercial space programs in the early 2000s, you know, helped take the space industry from something that was directed by NASA and produce the world-leading commercial space industry that we have today. Government investment, government capital, and government, you know, commitments catalyzed commercial investment in space. And I think that is the best model to look at in terms of how the fusion industry should evolve. Of course, we have the DOE milestone program, which is very well conceived and very well structured from a technical perspective, but underfunded. If I remember my math correctly, the commercial space program was authorized by Congress at $600 million for two companies, for SpaceX and someone else. And the milestone program, the initial funding was $50 million for 8 companies. So the scale of government investment is pretty small in comparison to the potential for fusion, especially for commercial space. And as we think about competition at the international level between the US and China and other organizations, the Commercial Crew Program is one reason why we have a commercial space industry in the US that's world leading. China, of course, is continuing to invest in fusion and providing the kind of public support for the fusion sector that the US once did for space. I think we should all hope that the US government continues to apply the same successful model at a much higher level of funding to continue to catalyze private investment in fusion. And one final point I'll make on that. Fusion is commercially compelling on its own, right? We don't absolutely need government support. I think the area where government support can help is to accelerate the development path of all the private companies, right? If we're raising money entirely from venture capital and private investors, we're pursuing a very serialized sort of risk burn down approach where we have to take the highest technical risk and sort of demonstrate it and raise more money and keep going. And the scale of the capital required at each stage goes up. In parallel, there's a lot of technology development that you need to actually build a commercial plant. It's not necessarily high risk, but it costs money. And probably the biggest role for public capital is to encourage private companies to be doing parallel technology development to ensure that they're ready for a commercial plant when the critical science, technical, physics risk is eliminated. Because otherwise, the chances pure private capital gets us to a physics demonstration in the early 2030s, but there's still a long timeline before you can actually build a plant.
Great point. John, on the supply chain, what are your thoughts on the matter?
Yeah, I was going to want to jump in there regardless. Yeah, I think exactly what applies to those companies in terms of the development programs, that's exactly what's true for the supply chain companies. I mentioned this before in terms of this idea of normalization, or all of the fusion companies giving some sort of milestone or trajectory to say, hey, here's where we're going to be at different dates, here's how much demand we need, things like that, just to build the confidence for supply chain companies to invest in development. I think government just as well could initialize this through things like just general risk mitigation, like a loan guarantee or credit support program, to effectively allow these smaller supply chain companies to build up. One of the biggest things that I've seen popping up recently that seems to work pretty well is like matching grants for equipment upgrades for manufacturing. It just opens the door to those early developmental needs that companies need to just get off the ground, especially when fusion is going to take 10 more years to really see the return on investment.
Brian, what are your thoughts from your perspective?
Yeah, the DOE milestone program is really key. And as alluded to by Alex, and providing a little bit more context here, space launch worked really well pre-SpaceX, pre-COTS. We had a successful government-run program here in the United States. And then there was a moment when it was decided that the privatization of an industry was in order. And NASA COTS, this program emerged to help transition it from government functional groups to private industry very successfully with SpaceX and now a wave of space launch companies that have commercialized. The milestone program, of which since some of us are part of the 8 awardees, Thea is as well, was a very deep dive on the technical basis to understand the viability of an architecture, and then set up a program where taxpayer dollars were not at risk, that the companies must hit their milestones before funds were released. So did so in a very risk-averse way to commercialize fusion. But then, as alluded to before, the program did not receive the substantial funding that it actually needs to commercialize. So it's a great framework, but to actually commercialize fusion, power plants, these are billion-dollar assets. So a $50 million pool of money across 8 companies is a great start. But if we want to compete, and if we want to compete on the world stage, that needs to be billions of dollars. And billions of dollars is the scale that is relevant to a power plant, not specific to any company here. That is what these power plant assets for any technology, especially first of a kind, are. And so what we're seeing across the world right now is the governments of the world realizing this. And programs across the world mirroring what we should be doing in the United States to support the commercialization effort of fusion. So I think we have the framework. We're excited to hopefully get that support that we need so we can continue to be a leader in commercializing fusion here in the United States. That's the opportunity ahead of us.
Excellent. I know it's funny because as part of one article I wrote a while ago, I looked at the cost, how much investment had been put into Rivian, okay, an EV company, and not the first EV company, right? By the time that they did their IPO, it was about $4.5 billion, right? Which is, for a product that's significantly less risky than, say, fusion is. Well, what are you seeing on your side?
I'm sorry, I actually I have to run right now. I have a hard stop at 1. So, but thank you very much for having us. I appreciate it.
Sorry, Odette, what are your views? And given you have a different government, so it could be a slightly different answer.
The problem, yeah, but I have the same disappointment. I concur with my U.S. colleagues regarding the amount of investment from my government as well. And I'm pushing them to put more money in a strategic kind of a plan specifically for fusion. But I think one of the things that if we take a zoom out on this, this is a strategic race. At least we're talking about a strategic race. And strategy is what governments need to do. And if they want to win, they need to be able to execute on those strategic plans and create the right policies and real plans. I would rather call it a collaborative race, and I did a piece in the Hill recently regarding that kind of race and collaborative race that I think we're having. And we see today the U.S., and I would like to see the U.S. leading more strongly in that manner. But we can see that obviously China is pushing very, very strongly. And I think we should take our countries or make them more take accountability on the fact that they want energy. Energy is almost everything on national security level, on the defense, on national security and energy resiliency. And if they want to have it, they don't only need to talk about it, but they need to execute on it. And I think we need to be helping them, explaining them why it's the right path to push and enable fusion to move faster.
Excellent. Alain, what are your thoughts on this one?
Yeah, so as you can understand, my perspective is an international one, so I will certainly not comment on what US DOE or what even Israel should do. First, a couple of remarks. First of all, let's remember that the governments have supported fusion for the past 70 years already. Okay, so it's not that we shouldn't forget about that. If we are here to talk and to discuss this point, is because governments have supported fusion for very, very long. And the paroxysm being the ITER project, but let's not forget about all what is accompanying fusion in all the countries that are today working on fusion. So that's very important. Second, again, we are at this stage where we transit from labs to industry. So the roles of government, I buy the question of strategy, is to make it possible. So is to ensure this transition, this public-private partnership to develop from public to private. But there will be a long time when this public-private partnership should exist, and they will support this. But progressively, of course, giving the floor to industry and to competition and so on and so forth. Last but not least, we mentioned the education and so on. I think one of the biggest role of the government is to make sure that the education goes with. So they have to make sure that our students are educated They have to make sure that our population is educated so that the people wait for it, accept this kind of energy source when it comes a reality. And last but not least, they have to educate themselves, because it's very, very difficult very often it's very difficult to talk to a minister, to somebody, to a decision maker who is not educated in what we are doing and doesn't understand the ins and outs, doesn't understand what time scale is, doesn't understand what an order of magnitude is, and so on and so forth. So we are in a very technical domain. And yes, the governments have to also understand what we are doing, I would say.
Excellent. Ben, go ahead. It looks like you have a...
Yeah, a little different twist on it, right? So we've been talking a lot about like this fusion need right now, but I think there's also what a fusion power plant's going to need in the future. If you look in the United States, the markets that we're entering into are starting to be more and more impacted by policy decisions that are going to put intermittent resources that are going to change the market dynamics. And that even today, like the current like capacity market structures that incentivize clean, firm power, which is needed for reliable, resilient grids and an affordable energy transition, those market signals aren't adequate to support driving new capital investments. And so I think as we think about things that are going to be needed, recognizing the attributes of fusion and having structures that support them being a part of our grid is going to be more and more important, which is low marginal cost assets, which is high capital balance sheets for recovery. So we're going to do something a little bit different to think about economic market conditions.
You're on mute, Mike.
Sorry, saying go ahead. It looks like you have something.
Yeah. No, so I just forgot one point, and I absolutely must bring it back here, in particular here on the governmental roles. It's the question of the regulation, of the nuclear regulation. So I know we have different approaches, different views, and so on. But if we ever want to deploy fusion all over the planet and to sell it, and not only to our own countries and so on, we need to continue the discussion at the highest levels, and I think the IAEA is very well suited for that, in order to set up a regulation. There are several paths, at least to start with. I can understand the path that UK or US is trying to follow. I can tell you that the European countries, in particular France, will not follow this path. Who don't care. I mean, we have to end up with one safety case which is suited for fusion. So whatever the point we are starting with, I mean, we need to continue discussing at the governmental levels in order to have an acceptability of fusion all over the world when it's ready. This is very important, including the waste and so on. But simply the regulation is a very important point that shouldn't be left at the end or shouldn't be neglected at this particular stage, because we are setting up machines which have a very low amount of tritium or whatever to make the demonstration.
Excellent. Brian, go ahead.
Yeah, now I spent a couple of minutes talking about the mechanics of how government support could work, but didn't spend enough time talking about why. As evidenced by these multiple countries of the world putting billions of dollars to focus on commercialization of fusion, I think one of the main reasons why that's happening is because they see fusion technology, the actual technology itself, as well as the deployment of it for the creation of a lot of baseload power. They see those two things as very strategic to their countries, their economies, their future. So I think focusing on here in the United States, where I'm sitting, United States, we've very efficient capital markets. So that has been a great leader for now, you know the numbers better than I do, Mike, the 50 or so fusion companies here, even a lot of which are in the United States, to start and to flourish. Using the naphtha COTS as an example, where this milestone program or other government support that we see across the world can really help, is to minimize timelines. It's taking something that's already well underway and adding fuel to the fire to say, okay, private capital markets were to support this, as mentioned by a couple of people on this call. Like, you could stage it, you could buy down some risk and take some time, or you could supercharge it. And we're in the stage that the governments of the world are now supercharging it. So that's an opportunity for countries to really lock in technology and economic advantage for extended periods of time. Potentially, it's the most important technology that the world will ever touch. So I think that's the opportunity, and that's why these programs, especially in the United States, should really be firmly supported in the near term.
So more nitrous oxide or lighter fluid, depending on which analogy you like. Let's jump to some of the questions here from the audience. So there's one, I'll try to paraphrase these because some are a little bit long. There's one from a person in a supply chain company that said, what are your strategies to align supply chain readiness with your project milestones? Ben, why don't we go to you guys first, and we'll kind of just go around, spend a minute each on it.
Yeah, I mean, this is fundamental project management behaviors where you lay out the long lead times for your parts, you overlay those with your schedules, and provide yourself sufficient margin. In order to know that information, though, you have to be very engaged with the suppliers. I'm incredibly impressed with the way we staff up procurement engineering function here that can integrate with our suppliers and help us understand their situations better, and then have relationship managers that are able to manage those relationships through these challenging early stages. But you really just have to get far enough ahead of it and understand what it's going to take to make this stuff happen.
So dig in and do the normal supply chain things, basically. Sounds like to a large extent. Alex, what are you thinking on your side?
Yeah, so I think there's two prongs. One is what Ben said, right? There's first understanding the problem and sort of mapping things out and figuring what the lead times are, where the pain points are. I think what we're looking at Xcimer is how do we help suppliers find opportunities for commonality? Because both it lets them spread their own risk and their own decision making among multiple companies. I'm sure no supplier wants to be in the position of having to decide which of 65 fusion companies is going to be successful and which one they should invest in building out capacity for. And so helping suppliers understand the fusion market and understand like where their efforts are best invested and where they'll get the best return is something we spend time on. I think this is also a really important area that we talk to the Department of Energy about and other governmental bodies as well. I think in addition to the the advantages we talked about of public funding for the milestone program, or other venues to help accelerate companies with their own roadmaps, public investment in the supply chain, and I think someone mentioned earlier loan guarantees and models that have been successful in other industries are really potentially important for fusion. And so that's sort of our approach is trying to help catalyze sort of a broader movement among suppliers and among the industry, and help them understand how their efforts can support the entire industry so that they're not tied specifically to one company's technology, one company's roadmap.
Brian, how about yourself? What are you guys doing at Thea in this respect?
Yeah, so it's been a real pleasure actually getting to integrate Thea Energy and our tech development roadmap with industrial partners. So there are some things that we're getting really good at doing internal to our walls, but there are plenty of things where we can not have to focus on recreating the wheel by collaborating. So Ben made a great point. You need some just serious programmatic management and execution chops to begin with. You need to understand what is critical path, when you need stuff delivered for a multi-year project, but then within that context, be able to just openly communicate it with your partners external to the company and actually work to develop something that is a win-win for both parties. And that's, I think, the cool opportunity that Fusion has.
Okay, Oded, what are your thoughts on this?
Yeah, I think one of the important thing in a compact system that allows us to move faster in terms of R&D is also relevant to the later stage. But at this stage, multiple suppliers, and I agree with what has been said, is some of what the things that we're doing, and long-term relationships with these multiple suppliers, machining and manufacturing and things like that. And also, if there's an R&D part in what we are asking our suppliers to do, then we're adding and looking for grants and government support to show that this is an ecosystem and actually create an ecosystem around what we're doing. I think that encourages them to work with us and creates the understanding that this is a long-term thing and it's coming. And that's the message, and really build with them the excitement that we have. And join us in this path in solving the energy element with fusion. So creating excitement and buying as well as helping in that term.
Alain, obviously your organization has been doing this for a very long time, at least in the fusion world, perhaps longer than anybody else. What are your lessons learned on this one?
Okay, I will not add, I'll repeat the same thing. I think one of the lessons that we are learning today, that we have been learning along the construction of ITER in a sense, is that really, yes, if you want to go to industry, if you want to have industry very close to you, they have to be involved from the very, very beginning, from the concept. This is obvious that the ITER, for instance, is really the result of the labs, but at the same time is really connecting to a very, very, very large industry network and so on. And we continue seeing clashes of culture here. You don't do this like this, you don't do this like that, and so on. So if we really are serious now, and I was mentioning the question of the integrator before, we really need to work with the biggest energy industries, in particular nuclear industries, to start with, and to conceive reactors from the very beginning with all the aspects of maintainability. I mean, it's not a joke. ITER is too small. ITER is too small. The maintenance of ITER will be a nightmare. The building of ITER is in fact too small, okay? So that's fine. It will not be fine as a reactor because you need much more room for and much more access to maintain, to refurbish and so on. So ITER, in that respect, ITER is really still a research machine, a research facility, very clearly. So all these kind of things needs to be taken from the very beginning now, not only the way you scale the fabrication of gyrotrons, magnets or whatever, but really how you deal with a plant, with a power plant. That's something that is becoming more and more obvious these days.
John, as a supplier, what would you say to the companies? What would you kind of say? What's the best way to engage?
Yeah, I think it's exactly that. It is engaging. You know, this idea of trying to overlap our development timeline with the needs of the fusion companies' timelines. The only way we get that is by being told what their timeline is. Some people treat every development they do internally like it's, you know, the gold from Fort Knox. Other people are much more open about their developmental timelines. The ones that are more open only help the suppliers make sure we're aligned in the long term with what they need. I realize you don't want to give away all the trade secrets, but the more open these fusion companies are, I think the more success they'll have in bringing in integrators from the supply chain across the board. The one other comment I'll make, and I said this in my talk, was you know, diversification is really critical for us right now. Being able to work across multiple sectors, that's not just fusion. You know, Alex kind of made the point about not working with just one fusion company, but making sure you're ready for as many as you can because you don't know who's going to succeed. Out of 65, you know, maybe a few. But you know, going to other sectors, that's really what we're doing at Peak now, is making sure we can apply our same technology in as many places as possible. So we're not developing just for fusion at the end of the day. Maybe that gets us 80 to 90% of the fusion needs, and then we have a little 10% development window we have to go through. But yeah, kind of through those two prongs, I think that's really how we're trying to align our development strategies with the supply chain needs for fusion companies.
Excellent. Since we're running, this session is run kind of long, I'm going to cut it off. I'll send out the rest of the questions to everybody if you want to send me answers, and we'll get those to the people. But again, thank you very much, guys, for your expertise here. I always find these sort of things interesting. They bring up a lot of interesting points, and really appreciate your help on this. And thank you very much.
Thank you.
Thank you very much.
We will be sending out a link to the recording of this. So look for that in the next couple of days. If Zoom's faster, it'll be tomorrow. If it's not as fast, it'll be the day after tomorrow. It'll happen before they move.
Thanks, Mike.
Okay.
Thanks, everyone.
Awesome. Thank you for
very
organizing
much.
this.
Bye, everyone.
Cheers.